Kylie Ying has worked at many interesting places, such as MIT, CERN, and FreeCodeCamp. She's a physicist, engineer, and basically a genius. And now she's going to teach you about machine learning in a way that is accessible to absolute beginners.
What's up, you guys? So welcome to Machine Learning for Everyone. If you are someone who is interested in machine learning and you think you are considered as everyone, then this video is for you. In this video, we'll talk about supervised and unsupervised learning models. We'll go through maybe a little bit of the logic or math behind them, and then we'll also see how we can program it on Google Colab. If there are certain things that I have done and you're somebody with more experience than me, please feel free to correct me in the comments and we can all as a community learn from this together. So with that, let's just dive right in. Without wasting any time, let's just dive straight into the code and I will be teaching you guys concepts as we go. So this here is the UCI machine learning repository, and basically they just have a ton of data sets that we can access. And I found this really cool one called the Magic Gamma Telescope data set. So in this data set, if you don't want to read all of this information, to summarize what I think is going on, is there's this gamma telescope and we have all these high energy particles hitting the telescope. Now there's a camera, there's a detector that actually records certain patterns of how this light hits the camera, and we can use properties of those patterns in order to predict what type of particle caused that radiation. So whether it was a gamma particle or some other hadron. Down here, these are all of the attributes of those patterns that we collect in the camera. So you can see that there's, some length, width, size, asymmetry, etc. Now we're going to use all these properties to help us discriminate the patterns and whether or not they came from a gamma particle or a hadron. So in order to do this, we're going to come up here, go to the data folder, and you're going to click this Magic 04 data, and we're going to download that. Now over here, I have a Colab notebook open. So you go to colab.research.google.com, you start a new notebook, and I'm just going to call this the Magic data set. So actually, I'm going to call this FreeCodeCamp Magic example. Okay. So with that, I'm going to first start with some imports. So I will import, I always import NumPy. I always import pandas. And I always import matplotlib. And then we'll import other things as we go. So yeah. We run that. In order to run the cell, you can either click this play button here, or you can, on my computer, it's just Shift Enter, and that will run the cell. And here I'm just going to let you guys know, okay, this is where I found the data set. So I've copied and pasted this actually, but this is just where I found the data set. And in order to import that downloaded file that we got from the computer, we're going to go over here to this folder thing. And I am literally just going to drag and drop that file into here. Okay. So in order to take a look at, what does this file consist of? Do we have the labels? Do we not? I mean, we could open it on our computer, but we can also just do pandas read CSV, and we can pass in the name of this file. And let's see what it returns. So it doesn't seem like we have the labels. So let's go back to here. I'm just gonna make the columns, the column labels, all of these attribute names over here. So I'm just gonna take these values and make that the column names. All right, how do I do that? So basically, I will come back here and I will create a list called calls, and I will type in all of those things. With f size, f conc, and we also have f conc 1. We have f symmetry, fm3 long, FM3 trans, F alpha, what else do we have? F dist and class. And class, okay, great. Now, in order to label those as these columns down here in our data frame, so basically this command here just reads some CSV file that you pass in. CSV is comma separated values, and turns that into a pandas data frame object. So now if I pass in a names here, then it basically assigns these labels to the columns of this data set. So I'm gonna set this data frame equal to df. And then if we call, so head is just like, give me the first 5 things. Now you'll see that we have labels for all of these, okay? All right, great. So one thing that you might notice is that over here, the class labels, we have G and H. So if I actually go down here and I do data frame class.unique, you'll see that I have either G's or H's, and these stand for gammas or hadrons. And our computer is not so good at understanding letters, right? Our computer is really good at understanding numbers. So what we're going to do is we're going to convert this to 0 for G and 1 for H. So here I'm going to set this equal to this, whether or not that equals G. And then I'm just going to say as type int. So what this should do is convert this entire column. If it equals G, then this is true, so I guess that would be 1. And then if it's H, it would be false, so that would be 0. But I'm just converting G and H to 1s and 0s. It doesn't really matter like if G is 1 and H is 0 or vice versa. Let me just take a step back right now and talk about this data set. So here I have some data frame and I have all of these different values for each entry. Now this is each of these is one sample. It's one example. It's one item in our data set. It's one data point. All of these things are kind of the same thing when I mention, oh, this is one example or this is one sample or whatever. Now, each of these samples, they have, one quality for each or one value for each of these labels up here, and then it has the class. Now, what we're going to do in this specific example is try to predict for future, samples, whether the class is G for gamma or H for hadron. And that is something known as classification. Now, all of these up here, these are known as our features. And features are just things that we're going to pass into our model in order to help us predict the label, which in this case is the class column. So for, sample 0, I have 10 different features. So I have 10 different values that I can pass into some model, and I can spit out, the class, the label. And I know the true label here is G. So this is actually supervised learning. All right. So before I move on, let me just give you a quick little crash course on what I just said. This is machine learning for everyone. Well, the first question is, what is machine learning? Well, machine learning is a subdomain of computer science that focuses on certain algorithms which might help a computer learn from data without a programmer being there telling the computer exactly what to do. That's what we call explicit programming. So you might have heard of AI and ML and data science. What is the difference between all of these? So AI is artificial intelligence, and that's an area of computer science where the goal is to enable computers and machines to perform human-like tasks and simulate human behavior. Now, machine learning is a subset of AI that tries to solve one specific problem and make predictions using certain data. And data science is a field that attempts to find patterns and draw insights from data. And that might mean we're using machine learning. So all of these fields kind of overlap, and all of them might use machine learning. So there are a few types of machine learning. The first one is supervised learning. And in supervised learning, we're using labeled inputs. So this means whatever input we get, we have a corresponding output label in order to train models and to learn outputs of different new inputs that we might feed our model. So for example, I might have these pictures, okay? To a computer, all these pictures are pixels. They're pixels with a certain color. Now in supervised learning, all of these inputs have a label associated with them. This is the output that we might want the computer to be able to predict. So for example, over here, this picture is a cat, this picture is a dog, and this picture is a lizard. Now there's also unsupervised learning. And in unsupervised learning, we use unlabeled data to learn about patterns in the data. So here are my input data points. Again, they're just images, they're just pixels. Well, okay, let's say I have a bunch of these different pictures. And what I can do is I can feed all of these to my computer, and I might not, my computer's not gonna be able to say, oh, this is a cat, dog, and lizard in terms of, the output, but it might be able to cluster all of these pictures. It might say, hey, all of these have something in common. All of these have something in common, and then these down here have something in common. That's finding some sort of structure in our unlabeled data. And finally, we have reinforcement learning. And reinforcement learning, well, there's an agent that is learning in some sort of interactive environment based on rewards and penalties. So let's think of a dog. We can train our dog, but there's not necessarily, any wrong or right output at any given moment, right? Well, let's pretend that dog is a computer. Essentially what we're doing is we're giving rewards to our computer and telling our computer, hey, this is probably something good that you want to keep doing. Well, computer agent, terminology. But in this class today, we'll be focusing on supervised learning and unsupervised learning and learning different models for each of those. All right, so let's talk about supervised learning first. So this is kind of what a machine learning model looks like. You have a bunch of inputs that are going into some model, and then the model is spitting out an output, which is our prediction. So all these inputs, this is what we call the feature vector. Now, there are different types of features that we can have. We might have qualitative features, and qualitative means categorical data. There's either a finite number of categories or groups. So one example of a qualitative feature might be gender. And in this case, there's only two here. It's for the sake of the example. I know this might be a little bit outdated. Here we have a girl and a boy. There are two genders, there are two different categories. That's a piece of qualitative data. Another example might be, okay, we have, a bunch of different nationalities. Maybe a nationality or a nation or a location. That might also be an example of categorical data. Now, in both of these, there's no inherent order. It's not like, we can rate US 1 and France 2, Japan 3, etc., right? There's not really any inherent order built into either of these categorical data sets. That's why we call this nominal data. Now, for nominal data, the way that we want to feed it into our computer is using something called one-hot encoding. So let's say that, I have a data set. Some of the items in our data, some of the inputs might be from the US. Some might be from India, then Canada, then France. Now, how do we get our computer to recognize that? We have to do something called one-hot encoding. And basically, one-hot encoding is saying, okay, well, if it matches some category, make that a 1, and if it doesn't, just make that a 0. So for example, if your input were from the US, you might have 1, 0, 0, 0. India, 0, 1, 0, 0. Canada, okay, well, the item representing Canada is 1, and then France, the item representing France is 1, and then you can see that the rest are zeros. That's one-hot encoding. Now, there are also a different type of qualitative feature. So here on the left, there are different age groups. There's babies, toddlers, teenagers, young adults, and so on, right? And on the right-hand side, we might have different ratings. So maybe bad, not so good, mediocre, good, and then like great. Now, these are known as ordinal pieces of data because they have some sort of inherent order, right? Like being a toddler is a lot closer to being a baby than being an elderly person, right? Or good is closer to great than it is to really bad. So these have some sort of inherent ordering system. And so for these types of data sets, we can actually just mark them from 1 to 5, or we can just say, hey, for each of these, let's give it a number. And this makes sense because, like, for example, the thing that I just said, how good is closer to great than good is close to not good at all. Well, 4 is closer to 5 than 4 is close to 1. So this actually kind of makes sense. And it'll make sense for the computer as well. All right, there are also quantitative pieces of data. And quantitative pieces of data are numerical valued pieces of data. So this could be discrete, which means, they might be integers, or it could be continuous, which means all real numbers. So for example, the length of something is a quantitative piece of data. It's a quantitative feature. The temperature of something is a quantitative feature. And then maybe how many Easter eggs I collected in my basket this Easter egg hunt, that is an example of discrete quantitative feature. Okay, so these are continuous, and this over here is discrete. So those are the things that go into our feature vector. Those are our features that we're feeding this model, because our computers are really, really good at understanding math, right? At understanding numbers. They're not so good at understanding things that humans might be able to understand. Well, what are the types of predictions that our model can output? So in supervised learning, there are some different tasks. There's one, classification. And basically classification just saying, okay, predict discrete classes. And that might mean, this is a hot dog, this is a pizza, and this is ice cream. Okay, so there are 3 distinct classes, and any other pictures of hot dogs, pizza, or ice cream, I can put under these labels. Hot dog, pizza, ice cream. This is something known as multi-class classification. But there's also binary classification. And binary classification, you might have hot dog or not hot dog. So there's only 2 categories that you're working with, something that is something and something that isn't. Binary classification. Okay, so yeah, other examples. So if something has positive or negative sentiment, that's binary classification. Maybe you're predicting your pictures if they're cats or dogs. That's binary classification. Maybe, you are writing an email filter and you're trying to figure out if an email is spam or not spam. So that's also binary classification. Now for multi-class classification, you might have, cat, dog, lizard, dolphin, shark, rabbit, etc. We might have different types of fruits, so like orange, apple, pear, etc. And then maybe different plant species. But multi-class classification just means more than 2. Okay, and binary means we're predicting between 2 things. There's also something called regression when we talk about supervised learning. And this just means we're trying to predict continuous values. So instead of just trying to predict different categories, we're trying to come up with a number that, is on some sort of scale. So some examples. Some examples might be the price of Ethereum tomorrow. Or it might be, okay, what is going to be the temperature? Or it might be, what is the price of this house? Right? So these things don't really fit into discrete classes. We're trying to predict a number that's as close to the true value as possible using different features of our data set. So that's exactly what our model looks like in supervised learning. Now let's talk about the model itself. How do we make this model learn? Or how can we tell whether or not it's even learning? So before we talk about the models, let's talk about how can we actually like evaluate these models, or how can we tell whether something is a good model or a bad model. So let's take a look at this data set. So this data set this is from a Pima Indian diabetes data set. And here we have different number of pregnancies, different glucose levels, blood pressure, skin thickness, insulin, BMI, age, and then the outcome, whether or not they have diabetes. 1 for they do, 0 for they don't. So here, all of these are quantitative features, right? Because they're all on some scale. So each row is a different sample in the data. So it's a different example. It's one person's data, and each row represents one person in this data set. Now this column, each column represents a different feature. So this one here is some measure of blood pressure levels. And this one over here, as we mentioned, is the output label. So this one is whether or not they have diabetes. And as I mentioned, this is what we would call a feature vector, because these are all of our features in one sample. And this is what's known as the target, or the output for that feature vector. That's what we're trying to predict. And all of these together is our features matrix, X. And over here, this is our labels or targets vector, Y. So I've condensed this to a chocolate bar to kind of talk about some of the other concepts in machine learning. So over here we have our X, our features matrix, and over here this is our label Y. So each row of this will be fed into our model, right? And our model will make some sort of prediction. And what we do is we compare that prediction to the actual value of Y that we have in our labeled data set, because that's the whole point of supervised learning, is we can compare what our model is outputting to, oh, what is the truth actually? And then we can go back and we can adjust some things so that the next iteration we get closer to what the true value is. So that whole process here, the tinkering, okay, what's the difference? Where did we go wrong? That's what's known as training the model. Okay, so take this whole, chunk right here. Do we want to really put our entire chocolate bar into the model to train our model? Not really, right? Because if we did that, then how do we know that our model can do well on new data that we haven't seen? Like if I were to create a model to predict whether or not someone has diabetes, let's say that I just train all my data and I see that on my training data it does well. I go to some hospital, I'm like, here's my model. I think you can use this to predict if somebody has diabetes. Do we think that would be effective or not? Probably not, right? Because we haven't assessed how well our model can generalize. Okay, it might do well after, our model has seen this data over and over and over again, but what about new data? Can our model handle new data? Well, how do we get our model to assess that? So we actually break up our whole data set that we have into 3 different types of data sets. We call it the training data set, the validation data set, and the testing data set. And you might have 60% here, 20% and 20%, or 80, 10, and 10. It really depends on how many statistics you have. I think either of those would be acceptable. So what we do is then we feed the training data set into our model. We come up with, this might be a vector of predictions corresponding with each sample that we put into our model. We figure out, okay, what's the difference between our prediction and the true values? This is something known as loss. Loss is, what's the difference here in some numerical quantity, of course. And then we make adjustments, and that's what we call training, okay? So then once, we've made a bunch of adjustments, we can put our validation set through this model. And the validation set is kind of used as a reality check during or after training to ensure that the model can handle unseen data still. So every single time after we train one iteration, we might stick the validation set in and see, hey, what's the loss there? And then after our training's over, we can assess the validation set and ask, hey, what's the loss there? But one key difference here is that we don't have that training step. This loss never gets fed back into the model, right? That feedback loop is not closed. All right, so let's talk about loss really quickly. So here I have 4 different types of models. I have some sort of data that's being fed into the model and then some output. Okay, so this output here is pretty far from, this truth that we want. And so this loss is going to be high. In model B, again, this is pretty far from what we want, so this loss is also going to be high. Let's give it 1.5. Now this one here, it's pretty close. I mean, maybe not almost, but pretty close to this one. So that might have a loss of 0.5. And then this one here is maybe further than this, but still better than these two. So that loss might be 0.9. Okay, so which of these model performs the best? Well, model C has the smallest loss, so it's probably model C. Okay, now let's take model C after, we've come up with all these models and we've seen, okay, model C is probably the best model. We take model C and we run our test set through this model. And this test set is used as a final check to see how generalizable that chosen model is. So if I, finish training my diabetes data set, then I could run it through some chunk of the data and I can say, oh, like this is how it would perform on data that it's never seen before at any point during the training process, okay? And that loss, that's the final reported performance of my test set, or this would be the final reported performance of my model, okay? So let's talk about this thing called loss, because I think I kind of just glossed over it, right? So loss is the difference between your prediction and the actual label. So this would give a slightly higher loss than this. And this would even give a higher loss because it's even more off. In computer science, we like formulas, right? We like formulaic ways of describing things. So here are some examples of loss functions and how we can actually come up with numbers. This here is known as L1 loss. And basically L1 loss just takes the absolute value of whatever your, real value is, whatever the real output label is, subtracts the predicted value and takes the absolute value of that, okay? So the absolute value is a function that looks something like this. So the further off you are, the greater your loss is, right? In either direction. So if your real value is off from your predicted value by 10, then your loss for that point would be 10. And then this sum here just means, hey, we're taking all the points in our data set and we're trying to figure out the sum of how far everything is. Now, we also have something called L2 loss. So this loss function is quadratic, which means that if it's close, the penalty is very minimal. And if it's off by a lot, then the penalty is much, much higher, okay? And this, instead of the absolute value, we just square the difference between the two. Now there's also something called binary cross entropy loss. It looks something like this, and this is for binary classification. This might be the loss that we use. So this loss, I'm not gonna really go through it too much, but you just need to know that loss decreases as the performance gets better. So there are some other measures of performance as well. So for example, accuracy. What is accuracy? So let's say that these are pictures that I'm feeding my model, okay? And these predictions might be apple, orange, orange, apple. Okay, but the actual is apple, orange, apple, apple. So 3 of them were correct and 1 of them was incorrect. So the accuracy of this model is 3/4 or 75%. All right, coming back to our Colab notebook, I'm going to close this a little bit. Again, we've imported stuff up here. And we've already created our data frame right here. And this is all of our data. This is what we're going to use to train our models. So down here, again, if we now take a look at our data set, you'll see that our classes are now 0s and 1s. So now this is all numerical, which is good because our computer can now understand that. Okay. And you know, it would probably be a good idea to maybe kind of plot, hey, do these things have anything to do with the class? So here, I'm going to go through all of the labels. So for label in the columns of this data frame, so this just gets me the list. Actually, we have the list, right? It's called, so let's just use that. It might be less confusing. Of everything up till the last thing, which is the class. So I'm going to take all these 10 different features and I'm going to plot them as a histogram. And now I'm going to plot them as a histogram. So basically, if I take that data frame and I say, okay, for everything where the class is equal to 1, so these are all of our gammas, remember. Now, for that portion of the data frame, if I look at this label, so now these, okay, what this part here is saying is inside the data frame, get me everything where the class is equal to 1. So that's all of these would fit into that category, right? And now let's just look at the label column. So the first label would be f length, which would be this column. So this command here is getting me all the different values that belong to class 1 for this specific label. And that's exactly what I'm going to put into the histogram. And now I'm just going to tell, you know, matplotlib, make the color blue, label this as, you know, gamma, set alpha, why do I keep doing that? Alpha equal to 0.7, so that's just like the transparency. And then I'm going to set density equal to true, so that when we compare it to the hadrons here, we'll have a baseline for comparing them. Okay, so the density being true just basically normalizes these distributions. So, you know, if you have 200 of one type and then 50 of another type, well, if you drew the histograms, it would be hard to compare because one of them would be a lot bigger than the other, right? But by normalizing them, we kind of are distributing them over how many samples there are. All right, and then I'm just going to put a title on here, make that the label, the Y label. So because it's density, the Y label is probability. And the X label is just gonna be the label. What is going on? And I'm going to include a legend, and plt.show just means, okay, display the plot. So if I run that, just be up to the last item. So we want a list, right? Not just the last item. And now we can see that we're plotting all of these. So here we have the length. Oh, and I made this gamma. So this should be hadron. Okay. So the gamma's in blue, the hadrons are in red. So here we can already see that, you know, maybe if the length is smaller, it's probably more likely to be gamma, right? And we can kind of, you know, these all look somewhat similar. But here, okay, clearly if there's more asymmetry, or if, you know, this asymmetry measure is larger, then it's probably a hadron. Okay, oh, this one's a good one. So F alpha, seems like hadrons are pretty evenly distributed, whereas if this is smaller, it looks like there's more gammas in that area. Okay, so this is kind of what the data that we're working with. We can kind of see what's going on. Okay, so the next thing that we're going to do here is we are going to create our train, our validation, and our test data sets. So I'm going to set train, valid, and test to be equal to this, so numpy.split, I'm just splitting up the data frame. And if I do this sample where I'm sampling everything, this will basically shuffle my data. Now, if I want to pass in where exactly I'm splitting my data set, so the first split is going to be maybe at 60%. So I'm just going to say 0.6 times the length of this data frame. So, and then cast that to an integer. That's going to be the first place where, you know, I cut it off, and that'll be my training data. Now, if I then go to 0.8, this basically means everything between 60% and 80% of the length of the data set will go towards validation. And then like everything from 80 to 100 is going to be my test data. So I can run that. And now if we go up here and we inspect this data, we'll see that these columns seem to have values in like the 100s, whereas this one is 0.03. Right, so the scale of all these numbers is way off, and sometimes that will affect our results. So one thing that we would want to do is scale these so that they are, you know, so that it's now relative to maybe the mean and the standard deviation of that specific column. I'm going to create a function called scale dataset. And I'm going to pass in the data frame. And that's what I'll do for now. Okay, so the X values are going to be, you know, I take the data frame, and let's assume that the columns are going to be, you know, that the label will always be the last thing in the data frame. So what I can do is say data frame dot columns all the way up to the last item, and get those values. Now for my Y, well, it's the last column, so I can just do this. I can just index into that last column and then get those values. Now, so I'm actually going to import something known as the standard scaler from sklearn. So if I come up here, I can go to sklearn.preprocessing, and I'm going to import standard scaler. I have to run that cell. I'm going to come back down here, and now I'm going to create a scaler and use that scaler. So standard scaler. And with the scaler, what I can do is actually just fit and transform X. So here I can say X is equal to scaler.fit transform X. So what that's doing is saying, okay, take X and fit the standard scaler to X, and then transform all those values, and what would it be? And that's going to be our new X. All right. And then I'm also going to just create, you know, the whole data as one huge 2D NumPy array. And in order to do that, I'm going to call hstack. So hstack is saying, okay, take an array and another array and horizontally stack them together. That's what the H stands for. So by horizontally stack them together, just like put them side by side, okay, not on top of each other. So what am I stacking? Well, I have to pass in something so that it can stack X and Y. And now, okay, so NumPy is very particular about dimensions, right? So in this specific case, our X is a two-dimensional object, but Y is only a one-dimensional thing. It's only a vector of values. So in order to now reshape it into a 2D item, we have to call numpy.reshape, and we can pass in the dimensions of its reshape. So if I pass in -1, 1, that just means, okay, make this a 2D array, where the -1 just means infer what this dimension value would be, which ends up being the length of y. This would be the same as literally doing this, but the negative one is easier because we're making the computer do the hard work. So if I stack that, I'm going to then return the data, x and y. Okay. So one more thing is that if we go into our training data set, okay, again, this is our training data set, and we get the length of the training data set, but where the training data set's class is 1. So remember that this is the gammas. And then if we print that, and we do the same thing but 0, we'll see that, you know, there's around 7,000 of the gammas, but only around 4,000 of the hadrons. So that might actually become an issue. And instead, what we want to do is we want to oversample our training data set. So that means that we want to increase the number of these values so that these kind of match better. And surprise, surprise, there is something that we can import that will help us do that. So I'm going to go to from imlearn.oversampling, and I'm going to import this random oversampler. Run that cell and come back down here. So I will actually add in this parameter called oversample and set that to false for default. And if I do want to oversample, then what I'm going to do, and by oversample, so okay, if I do want to oversample, then I'm going to create this ROS and set it equal to this random oversampler. And then for X and Y, I'm just going to say, okay, just fit and resample X and Y. And what that's doing is saying, okay, take more of the less class. So take the less class and keep sampling from there to increase the size of our data set of that smaller class so that they now match. So if I do this and I scale data set and I pass in the training data set where oversample is true. So this, let's say this is train and then X train, Y train. Oops, what's going on? Oh, these should be columns. So basically what I'm doing now is I'm just saying, okay, what is the length of Y train? Okay, now it's 14,800, whatever. And now let's take a look at how many of these are type 1. So actually we can just sum that up. And then we'll also see that if we instead switch the label and ask how many of them are the other type, it's the same value. So now these have been evenly, rebalanced. Okay, well, okay. So here I'm just going to make this the validation data set. And then the next one, I'm going to make this the test data set. All right, and we're actually going to switch oversample here to false. Now, the reason why I'm switching that to false is because my validation and my test sets are for the purpose of, if I have data that I haven't seen yet, how does my sample perform on those? And I don't want to oversample for that right now. Like I don't care about balancing those. I want to know if I have a random set of data that's unlabeled, can I trust my model, right? So that's why I'm not oversampling. I run that, and again, what is going on? Oh, it's because we already have this train. So I have to come up here and split that data frame again. And now let's run these. Okay. So now we have our data properly formatted. And we're going to move on to different models now, and I'm going to tell you guys a little bit about each of these models, and then I'm going to show you how we can do that in our code. So the first model that we're going to learn about is KNN, or K nearest neighbors. Okay, so here I've already drawn a plot On the y-axis, I have the number of kids that a family might have, and then on the x-axis, I have their income in terms of thousands per year. So, you know, if someone's making 40,000 a year, that's where this would be. And if somebody's making 320, that's where that would be. Somebody has 0 kids, it'd be somewhere along this axis. Somebody has 5, it'd be somewhere over here, okay? And now I have these plus signs and these minus signs on here. So what I'm going to represent here is the plus sign means that they own a car, and the minus sign is going to represent no car, okay? So your initial thought should be, okay, I think this is binary classification because all of our points, all of our samples have labels. So this is a sample with the plus label. And this here is another sample with the minus label. This is an abbreviation for width that I'll use. All right. So we have this entire data set, and maybe around half the people own a car, and maybe around half the people don't own a car. Okay, well, what if I had some new point? Let me choose a different color. I'll use this nice green. Well, what if I have a new point over here? So let's say that somebody makes 40,000 a year and has 2 kids. What do we think that would be? Well, just logically looking at this plot, you might think, okay, it seems like they wouldn't have a car, right? Because that kind of matches the pattern of everybody else around them. So that's the whole concept of this nearest neighbors is you look at, okay, what's around you? And then you're basically like, okay, I'm gonna take the label of the majority that's around me. So the first thing we have to do is we have to define a distance function. And a lot of times in, 2D plots like this, our distance function is something known as Euclidean distance. And Euclidean distance is basically just this straight line distance like this. Okay? So this would be the Euclidean distance. It seems like there's this point, there's this point, there's that point, etc. So the length of this line, this green line that I just drew, that is what's known as Euclidean distance. If we want to get technical with that, this exact formula is the distance. Here, let me zoom in. The distance is equal to the square root of one point's x minus the other point's x squared plus, extend that square root, the same thing for y. So y1 of 1 minus y2 of the other squared. Okay, so we're basically trying to find the length, the distances, the difference between x and y, and then square each of those, sum it up, and take the square root. Okay, so I'm gonna erase this so it doesn't clutter my drawing. But anyways, now going back to this plot. So here in the nearest neighbor algorithm, we see that there is a k, right? And this k is basically telling us, okay, how many neighbors do we use in order to judge what the label is? So usually we use a k of maybe, 3 or 5. Depends on how big our data set is. But here I would say maybe a logical number would be 3 or 5. So let's say that we take k to be equal to 3. Okay, well, of this data point that I drew over here, let me use green to highlight this. Okay, so of this data point that I drew over here, it looks like the 3 closest points are definitely this one, and then this one has a length of 4, and this one seems like it'd be a little bit further than 4. So actually these would be our 3 points. Well, all those points are blue. So chances are my prediction for this point is going to be blue. It's going to be, probably don't have a car. All right, now what if my point is somewhere, over here? Let's say that a couple has 4 kids and they make $240,000 a year. All right, well now my closest points are this one, probably a little bit over that one, and then this one, right? Okay, still all pluses. Well, this one is more than likely to be a plus, right? Now let me get rid of some of these just so that it looks a little bit more clear. All right, let's go through one more. What about a point that might be right here? Okay, let's see. Well, definitely this is the closest, right? This one's also closest. And then it's really close between the two of these. But if we actually do the mathematics, it seems like if we zoom in, this one is right here, and this one is in between these two. So this one here is actually shorter than this one. And that means that that top one is the one that we're going to take. Now, what is the majority of the points that are close by? Well, we have 1 plus here, we have 1 plus here, and we have 1 minus here, which means that the pluses are the majority. And that means that this label is probably somebody with a car. Okay? So this is how k nearest neighbors would work. It's that simple. And this can be extrapolated to further dimensions, to higher dimensions. You know, if you have, here we have 2 different features. We have the income, and then we have the number of kids. But let's say we have 10 different features. We can expand our distance function so that it includes all 10 of those dimensions. We take the square root of everything, and then we figure out which one is the closest to the point that we desire to classify, okay? So that's k nearest neighbors. So now we've learned about k nearest neighbors. Let's see how we would be able to do that within our code. So here I'm going to label the section k nearest neighbors. And we're actually going to use a package from sklearn. So the reason why we, use these packages is so that we don't have to manually code all of these things ourselves, because it would be really difficult, and chances are the way that we would code it either would have bugs or it'd be really slow, or I don't know, a whole bunch of issues. So what we're gonna do is hand it off to the pros. From here I can say, okay, from sklearn, which is this package .neighbors, I'm going to import k neighbors classifier because we're classifying, okay? So I run that, and our KNN model is going to be this k neighbors classifier, and we can pass in a parameter of how many neighbors, we want to use. So first, let's see what happens if we just use 1. So now if I do KNN model.fit, I can pass in my X training set and my Y train data, okay? So that effectively fits this model. And let's get all the predictions. So Y, KNN, or I guess, yeah, let's just do Y predictions. And my Y predictions are going to be KNN model.predict. So let's use the test set, X test, okay? All right, so if I call yPredict, you'll see that we have those, but if I get my truth values for that test set, you'll see that this is what we actually do. So just looking at this, we got 5 out of 6 of them. Okay, great. So let's actually take a look at something called the classification report that's offered by sklearn. So if I go to from sklearn.metrics, import classification report, what I can actually do is say, hey, print out this classification report for me. And let's check, I'm giving you the Y test and the Y prediction. We run this and we see we get this whole entire chart. So I'm gonna tell you guys a few things on this chart. All right, this accuracy is 82%, which is actually pretty good. That's just saying, hey, if we just look at, what each of these new points, what it's closest to, then we actually get an 82% accuracy, which means how many do we get right versus how many total are there. Now, precision is saying, okay, you might see that we have it for class 1 or class 0 and class 1. What precision is saying, let's go to this Wikipedia diagram over here because I actually kind of like this diagram. So here, this is our entire data set. And on the left over here, we have everything that we know is positive. So everything that is actually truly positive, that we've labeled positive in our original data set. And over here, this is everything that's truly negative. Now in this circle, we have things that are that were labeled positive by our model. On the left here, we have things that are truly positive because, this side is the positive side and this side is the negative side. So these are truly positive. Whereas all these ones out here, well, they should have been positive, but they were labeled as negative. And in here, these are the ones that we've labeled positive, but they're actually negative. And out here, these are truly negative. So precision is saying, okay, out of all the ones we've labeled as positive, how many of them are true positives? And recall is saying, okay, out of all the ones that we know are truly positive, how many did we actually get right? Okay. So going back to this over here, our precision score. So again, precision, out of all the ones that we've labeled as the specific class, how many of them are actually that class? It's 77 and 84%. Now recall how out of all the ones that are actually this class, how many of those did we get? This is 68% and 89%. All right, so not too shabby. We can clearly see that this recall and precision for like the class 0 is worse than class 1, right? So that means for hadrons, it's worse for hadrons than for our gammas. This F1 score over here is kind of a combination of the precision and recall score. So we're actually going to mostly look at this one because we have an unbalanced test data set. So here we have a measure of 72 and 87, or 0.72 and 0.87, which is not too shabby. All right. Well, what if we, made this 3? So we actually see that, okay, so what was it originally with 1? We see that our F1 score, is now, it was 0.72 and then 0.87. And then our accuracy was 82%. So if I change that to 3. All right, so we've kind of increased 0 at the cost of 1. And then our overall accuracy is 81. So let's actually just make this 5. All right. So, again, very similar numbers. We have 82% accuracy, which is pretty decent for a model that's relatively simple. Okay, the next type of model that we're going to talk about is something known as naive Bayes. Now, in order to understand the concepts behind naive Bayes, we have to be able to understand conditional probability and Bayes rule. So let's say I have some sort of data set that's shown in this table right here. People who have COVID are over here in this red row, and people who do not have COVID are down here in this green row. Now, what about the COVID test? Well, people who have tested positive are over here in this column, and people who have tested negative are over here in this column, okay? Yeah, so basically our categories are people who have COVID and test positive, people who don't have COVID but test positive, so a false positive, people who have COVID and test negative, which is a false negative, and people who don't have COVID and test negative, which, good, means you don't have COVID. Okay, so let's make this slightly more legible. And here in the margins, I've written down the sums of whatever it's referring to. So this here is the sum of this entire row, and this here might be the sum of this column over here. Okay, so the first question that I have is, what is the probability of having COVID given that you have a positive test? And in probability, we write that out like this. So the probability of COVID given, so this line, that vertical line, means given that, you know, some condition. So given a positive test. Okay, so what is the probability of having COVID given a positive test? So what this is asking is saying, okay, let's go into this condition. So the condition of having a positive test, that is this slice of the data, right? That means if you're in this slice of data, you have a positive test. So given that we have a positive test, given in this condition, in this circumstance, we have a positive test. So what's the probability that we have COVID? Well, if we're just using this data, the number of people that have COVID is 531. So I'm gonna say that there's 531 people that have COVID. And then now we divide that by the total number of people that have a positive test, which is 551. Okay, so that's the probability. And doing a quick division, we get that this is equal to around 96.4%. So according to this data set, which is data that I made up off the top of my head, so it's not actually real COVID data, but according to this data, the probability of having COVID, given that you tested positive, is 96.4%. All right, now with that, let's talk about Bayes' rule, which is this section here. Let's ignore this bottom part for now. So Bayes' rule is asking, okay, what is the probability of some event A happening given that B happened? So this we already know has happened. This is our condition, right? Well, what if we don't have data for that, right? Like, what if we don't know what the probability of A given B is? Well, Bayes' rule is saying, okay, well, you can actually go and calculate it as long as you have the probability of B given A, the probability of A, and the probability of B. Okay, and this is just a mathematical formula for that. All right, so here we have Bayes' rule. And let's actually see Bayes' rule in action. Let's use it on an example. So here, let's say that we have some disease statistics, okay? So not COVID, different disease. And we know that the probability of obtaining a false positive is 0.05. Probability of obtaining a false negative is 0.01. And the probability of the disease is 0.1. Okay, what is the probability of the disease given that we got a positive test? How do we even go about solving this? So what do I mean by false positive? What's a different way to rewrite that? A false positive is when you test positive, but you don't actually have the disease. So this here is a probability that you have a positive test given no disease, right? And similarly for the false negative, it's a probability that you test negative given that you actually have the disease. So if I put that into a chart, for example, and this might be my positive and negative tests, and this might be my diseases, disease and no disease. Well, the probability that I test positive but actually have no disease, okay, that's 0.05 over here. And then the false negative is up here for 0.01. So I'm testing negative, but I don't actually have the disease. So the probability that you test positive and you don't have the disease, plus the probability that you test negative given that you don't have the disease, that should sum up to 1. Okay, because if you don't have the disease, then you should have some probability that you're testing positive and some probability that you're testing negative, but that probability in total should be 1. So that means that the probability of negative and no disease, this should be the reciprocal. This should be the opposite. So it should be 0.95 because it's 1 minus whatever this probability is. And then similarly, up here, this should be 0.99 because the probability that we, test negative and have the disease plus the probability that we test positive and have the disease should equal 1. So this is our probability chart. And now this probability of disease being 0.1 just means I have a 10% probability of having the disease, right? Like in the general population, the probability that I have the disease is 0.1. Okay, so what is the probability that I have the disease given that I got a positive test? Well, remember that we can write this out in terms of Bayes' rule, right? So if I use this rule up here, this is the probability of a positive test given that I have the disease times the probability of the disease divided by the probability of the evidence, which is my positive test. All right, now let's plug in some numbers for that. The probability of having a positive test given that I have the disease is 0.99. And then the probability that I have the disease is this value over here, 0.1. Okay? And then the probability that I have a positive test at all should be, okay, what is the probability that I have a positive test given that I actually have the disease and then having the disease? And then the other case where the probability of me having a negative test positive test giving no disease times the probability of not actually having a disease. Okay, so I can expand that probability of having a positive test out into these two different cases. I have a disease and then I don't. And then what's the probability of having positive tests in either one of those cases? So that expression would become 0.99 times 0.1 plus 0.05, so that's the probability that I'm testing positive but don't have the disease, and then times the probability that I don't actually have the disease, so that's 1 minus 0.1. The probability that the population doesn't have the disease is 90%. So 0.9, and let's do that multiplication, and I get an answer of 0.6875 or 68.75%. Okay. All right, so we can actually expand that. We can expand Bayes' rule and apply it to classification. And this is what we call naive Bayes. So first, a little terminology. So the posterior is this over here because it's asking, hey, what is the probability of some class CK? So by CK, I just mean, the different categories. So C for category or class or whatever. So category 1 might be cats. Category 2, dogs. Category 3, lizards. All the way, we have K categories. K is just some number. Okay. So what is the probability of having this specific sample, X, so this is our feature vector of this one sample. What is the probability of X fitting into category 1, 2, 3, 4, whatever, right? So that's what this is asking. What is the probability that, it's actually from this class given all this evidence that we see, the X's? So the likelihood is this quantity over here. It's saying, okay, well, given that, assume that this class is class CK. Okay, assume that this is a category. Well, what is the likelihood of actually seeing X, all these different features from that category? And then this here is the prior. So like in the entire population of things, what are the probabilities? What is the probability of this class in general? Like if I have, in my entire data set, what is the percentage, what is the chance that this image is a cat? How many cats do I have, right? And then this down here is called the evidence, because what we're trying to do is we're changing our prior. We're creating this new posterior probability built upon the prior by using some sort of evidence, right? And that evidence is the probability of X. So that's some vocab. And this here is a rule for naive Bayes. Whoa. Okay, let's digest that a little bit, okay? So what is, let me use a different color. What is this side of the equation asking? It's asking, what is the probability that we are in some class K, CK, given that, this is my first input, this is my second input, this is, my third, fourth, this is my nth input. So let's say that our classification is, do we play soccer today or not? Okay, and let's say our X's are, okay, is it, how much wind is there? How much rain is there? And what day of the week is it? So let's say that it's raining, it's not windy, but it's Wednesday. Do we play soccer or do we not? So let's use Bayes' rule on this. So this here is equal to the probability of X1, X2, all these joint probabilities, given class K, times the probability of that class, all over the probability of this evidence. Okay? So what is this fancy symbol over here? This means proportional to. So how our equal sign means it's equal to, this like little squiggly sign means that this is proportional to. Okay? And this denominator over here, you might notice that it has no impact on the class. Like that number doesn't depend on the class, right? So this is going to be constant for all of our different classes. So what I'm gonna do is make things simpler. So I'm just going to say that this probability, X1, X2, all the way to Xn, this is going to be proportional to the numerator. I don't care about the denominator because it's the same for every single class. So this is proportional to X1, X2, Xn, given class K times the probability of that class. Okay, all right. So in naive Bayes, the point of it being naive is that we're actually, this joint probability, we're just assuming that all of these different things are all independent. So in my soccer example, the probability that we're playing soccer, or the probability that, it's windy and it's rainy and it's Wednesday, all of these things are independent. We're assuming that they're independent. So that means that I can actually write this part of the equation here as this. So each term in here, I can just multiply all of them together. So the probability of the first feature, given that it's class K, times the probability of the second feature, given that's class K, all the way up until, the nth feature of, given that it's class K. So this expands to all of this, all right? Which means that this here is now proportional to the thing that we just expanded times this. So I'm going to write that out. So the probability of that class, and I'm actually going to use this symbol. So what this means is it's a huge multiplication. It means multiply everything to the right of this. So this probability, X given some class K, but do it for all the i's. So I, what is I? Okay, we're going to go from the first xi all the way to the nth. So that means for every single I, we're just multiplying these probabilities together. And that's where this up here comes from. So to wrap this up, oops, this should be a line. To wrap this up in plain English, basically what this is saying is a probability that, we're in some category, given that we have all of these different features, is proportional to the probability of that class in general times the probability of each of those features given that we're in this one class that we're testing. So the probability of it, of us playing soccer today, given that it's rainy, not windy, and it's Wednesday, is proportional to, okay, well, what is the probability that we play soccer anyways? And then times the probability that it's rainy, given that we're playing soccer, times the probability that it's not windy, given that we're playing soccer. So how many times are we playing soccer when it's windy? And then how many times, or what's the probability that it's Wednesday, given that we're playing soccer? Okay. So how do we use this in order to make a classification? So that's where this comes in. Our y hat, our predicted y, is going to be equal to something called the argmax, and then this expression over here, because we want to take the argmax. Well, okay, if I write out this, again, this means the probability of being in some class CK given all of our evidence. Well, we're going to take the k that maximizes this expression on the right. That's what argmax means. So if k is in 1 through k, so this is how many categories there are, we're going to go through each k and we're going to solve this expression over here and find the k that makes that the largest. Okay? And remember that instead of writing this, we have now a formula, thanks to Bayes' rule, for helping us approximate that, right? And something that maybe we have like the evidence for that. We have the answers for that based on our training set. So this principle of going through each of these and finding whatever class, whatever category maximizes this expression on the right, this is something known as MAP for short, or maximum a posteriori. Pick the hypothesis, so pick the k that is the most probable so that we minimize the probability of misclassification. All right, so that is MAP. That is naive Bayes. Back to the notebook. So just like how I imported K-neighbors classifier up here, for naive Bayes, I can go to sklearn.naive Bayes, and I can import Gaussian naive Bayes. All right. And here I'm going to say my naive Bayes model is equal. This is very similar to what we had above. And I'm just going to say with this model, we are going to fit X train and Y train. All right, just like above. So this I might actually have to, so I'm going to set that. And exactly, just like above, I'm going to make my prediction. So here, I'm going to instead use my naive Bayes model. And of course, I'm going to run the classification report again. So I'm actually just going to put these in the same cell. But here we have the new Y prediction, and then Y test is still our original test data set. So if I run this, you'll see that, okay, what's going on here? We get worse scores, right? Our precision, for all of them, they look slightly worse. And our, for our precision, our recall, our F1 score, they look slightly worse for all the different categories. And our total accuracy, I mean, it's still 72%, which is not too shabby, but it's still 72%, okay? Which, is not that great. Okay, so let's move on to logistic regression. Here I've drawn a plot. I have Y, so this is my label on one axis, and then this is maybe one of my features. So let's just say I only have one feature in this case. It's X0, right? Well, we see that, I have a few of one class type down here, and we know it's one class type because it's 0, and then we have our other class type 1 up here, okay? So many of you guys are familiar with regression, so let's start there. If I were to draw a regression line through this, it might look something like this, right? Well, this doesn't seem to be a very good model. Like, why would we use this specific line to predict y, right? It's iffy, okay? For example, we might say, okay, well, it seems like, everything from here downwards would be one class type and here upwards would be another class type. But when you look at this, you visually can tell, okay, like that line doesn't make sense. Those dots are not along that line. And the reason is because we are doing classification, not regression. Okay. Well, first of all, let's start here. We know that this model, if we just use this line, it equals mx. So whatever this, let's just say it's x plus b, which is the y-intercept, right? And m is the slope. But when we use a linear regression, is it actually y hat? No, it's not, right? So when we're working with linear regression, what we're actually estimating in our model is a probability. What's a probability between 0 and 1 that is class 0 or class 1? So here, let's rewrite this as p equals mx plus b. Okay, well, mx plus b, that can range, from negative infinity to infinity, right? For any value of x, it goes from negative infinity to infinity. But probability, we know one of the rules of probability is that probability has to stay between 0 and 1. So how do we fix this? Well, maybe instead of just setting the probability equal to that, we can set the odds equal to this. So by that, I mean, okay, let's do probability divided by 1 minus the probability. Okay, so now it becomes this ratio. Now this ratio is allowed to take on infinite values. But there's still one issue here. Let me move this over a bit. The one issue here is that mx plus b, that can still be negative, right? Like if, I have a negative slope, if I have a negative b, if I have some negative x's in there, I don't know, but that's allowed to be negative. So how do we fix that? We do that by actually taking the log of the odds, okay? So now I have the log of, some probability divided by 1 minus the probability, and now that is on a range of negative infinity to infinity, which is good because the range of log should be negative infinity to infinity. Now, how do I solve for p, the probability? Well, the first thing I can do is take, I can remove the log by taking the e to the whatever is on both sides. So that gives me the probability over the 1 minus the probability is now equal to e to the mx plus b. Okay. So let's multiply that out. So the probability is equal to 1 minus probability e to the mx plus b. So p is equal to e to the mx plus b minus p times e to the mx plus b. And now we can move like terms to one side. So if I do p, so basically I'm moving this over, so I'm adding p. So now p, 1 plus e to the mx plus b is equal to e to the mx plus b. And let me change this parentheses, make it a little bigger. So now my probability can be e to the mx plus b divided by 1 plus e to the mx plus b. Okay, well, let me just rewrite this really quickly. I want a numerator of 1 on top. Okay, so what I'm going to do is I'm going to multiply this by negative mx plus b. And then also the bottom by negative mx plus b. And I'm allowed to do that because this over this is 1. So now my probability is equal to 1 over 1 plus e to the negative mx plus b. And now why do I rewrite it like that? It's because this is actually a form of a special function, which is called the sigmoid function. And for the sigmoid function, it looks something like this. So s of x, sigmoid, you know, at some x, is equal to 1 over 1 plus e to the negative x. So essentially what I just did up here is rewrite this in some sigmoid function where the x value is actually mx plus b. So maybe I'll change this to y just to make that a bit more clear. It doesn't matter what the variable name is, but this is our sigmoid function. And visually, what our sigmoid function looks like is it goes from 0, so this here is 0, to 1. And it looks something like this curved S, which I didn't draw too well. Let me try that again. This is hard to draw. Something, if I can draw this right, like that. Okay, so it goes in between 0 and 1. And you might notice that this form fits our shape up here. Oops, let's draw it sharper. But it fits our shape up there a lot better, right? All right, so that is what we call logistic regression. We're basically trying to fit our data to this sigmoid function, okay? And when we only have, you know, one data point, so if we only have one feature, x, then that's what we call simple logistic regression. But then if we have, you know, so that's only x0, but then if we have x0, x1, all the way to xn, we call this multiple logistic regression, because there are multiple features that we're considering when we're building our model. Logistic regression. So I'm going to put that here. And again, from sklearn, this linear model, we can import logistic regression, right? And just like how we did above, we can repeat all of this. So here, instead of NB, I'm gonna call this the log model, or LG logistic regression. I'm gonna change this to logistic regression. So I'm just going to use the default logistic regression. But actually, if you look here, you see that you can use different penalties. So right now we're using an L2 penalty, but L2 is our quadratic formula, okay? So that means that for, you know, outliers, it would really penalize that. For all these other things, you know, you can toggle these different parameters and you might get slightly different results. If I were building a production level logistic regression model, then I would want to go and I would want to figure out, you know, what are the best parameters to pass into here based on my validation data. But for now, we'll just use this out of the box. So again, I'm going to fit the X train and the Y train, and I'm just going to predict again. So I can just call this again. And instead of the LG, NB, I'm going to use LG. So here, this is decent. Precision 65%, recall 71, F1 68 or 82, total accuracy of 77. Okay, so it performs slightly better than naive Bayes, but it's still not as good as KNN. All right, so the last model for classification that I wanted to talk about is something called support vector machines, or SVMs for short. So what exactly is an SVM model? I have two different features, x0 and x1 on the axes. And then I've told you if it's, class 0 or class 1 based on the blue and the red labels. My goal is to find some sort of line between these two labels that best divides the data. All right, so this line is our SVM model. So I call it a line here because in 2D, it's a line, but in 3D, it would be a plane, and then you can also have more and more dimensions. So the proper term is actually, I wanna find the hyperplane that best differentiates these two classes. Let's see a few examples. Okay, so first, between these 3 lines, let's say A, B, and C, which one is the best divider of the data? Which one has, all the data on one side or the other? Or at least if it doesn't, which one divides it the most, right? Like which one has the most defined boundary between the two different groups? So this question should be pretty straightforward. It should be A, right? Because A has that clear, distinct line between where, everything on this side of A is one label, it's negative, and everything on this side of A is the other label, it's positive. So what if I have A, but then what if I had drawn my B like this, and my C maybe like this? Sorry, the labels are kind of close together. But now which one is the best? So I would argue that it's still A, right? And why is it still A? Because in these other two, look at how close this is to these points, right? So if I had some new point that I wanted to estimate, okay, say I didn't have A or B, so let's say we're just working with C. Let's say I have some new point that's right here, or maybe a new point that's right there. Well, it seems like just logically looking at this, I mean, without the boundary, that would probably go under the positives, right? I mean, it's pretty close to that other positive. So one thing that we care about in SVMs is something known as the margin. Okay, so not only do we want to separate the two classes really well, we also care about the boundary in between where the points in those classes in our data set are and the line that we're drawing. So in a line like this, the closest values to this line might be like here. And I'm trying to draw these perpendicular. Right? And so this effectively, if I switch over to these dotted lines, if I can draw this right. So these effectively are what's known as the margins. Okay, so these both here, these are our margins in our SVMs. And our goal is to maximize those margins. So not only do we want the line that best separates the two different classes, we want the line that has the largest margin. And the data points that lie on the margin lines, so basically these are the data points that's helping us define our divider. These are what we call support vectors. Hence the name support vector machines. Okay, so the issue with SVMs sometimes is that they're not so robust to outliers, right? So for example, if I had one outlier like this up here, that would totally change where I want my support vector to be, even though that might be my only outlier, okay? So that's just something to keep in mind as you're working with SVMs is it might not be the best model if there are outliers in your data set. Okay, so another example of SVMs might be, let's say that we have data like this. I'm just going to use a one-dimensional data set for this example. Let's say we have a data set that looks like this. Well, our, separator should be perpendicular to this line, but it should be somewhere along this line. So it could be anywhere like this. You might argue, okay, well, there's one here, and then you could also just draw another one over here, right? And then maybe you can have two SVMs, but that's not really how SVMs work. But one thing that we can do is we can create some sort of projection. So I realized here that one thing I forgot to do was to label where 0 was. So let's just say 0 is here. Now, what I'm going to do is I'm going to say, okay, I'm going to have x, and then I'm going to have x0 and x1. So x0 is just going to be my original x, but I'm going to make x1 equal to, let's say, x squared. So whatever is this squared, right? So now my negatives would be, maybe somewhere here, here, just pretend that it's somewhere up here. Right, and now my pluses might be something like that. And I'm gonna run out of space over here, so I'm just gonna draw these together, use your imagination. But once I draw it like this, well, it's a lot easier to apply a boundary, right? Now our SVM could be maybe something like this. And now you see that we've divided our data set. Now it's separable, where one class is this way and the other class is that way. Okay, so that's known as SVMs. I do highly suggest that, any of these models that we just mentioned, if you're interested in them, do go more in depth mathematically into them. Like how do we find this hyperplane, right? I'm not going to go over that in this specific course because you're just learning what an SVM is. But it's a good idea to know, oh, okay, this is the technique behind finding, what exactly are the how do you define the hyperplane that we're going to use? So anyways, this transformation that we did down here, this is known as the kernel trick. So when we go from x to some coordinate x and then x squared, what we're doing is we are applying a kernel. So that's why it's called the kernel trick. So SVMs are actually really powerful, and you'll see that here. So from sklearn.svm, we are going to import SVC. And SVC is our support vector classifier. So with this, with our SVM model, we are going to, create an SVC model. And we are going to, again, fit this to xtrain. I could have just copy and pasted this. I should have probably done that. Okay. Taking a bit longer. All right. Let's predict using our SVM model. And here, let's see if I can hover over this. All right, so again, you see a lot of these different parameters here that you can go back and change if you were creating a production level model. Okay, but in this specific case, we'll just use it out of the box again. So if I make predictions, you'll note that, wow, the accuracy actually jumps to 87% with the SVM. And even with class 0, there's nothing less than, 0.8, which is great. And for class 1, everything's at 0.9, which is higher than anything that we had seen to this point. So far we've gone over 4 different classification models. We've done SVMs, Logistic Regression, Naive Bayes, and KNN. And these are just simple ways on how to implement them. Each of these, they have different, hyperparameters that you can go and you can toggle, and you can try to see if that helps later on or not. But for the most part, they give us around 70 to 80% accuracy, okay, with SVM being the best. Now, let's see if we can actually beat that using a neural net. Now, the final type of model that I wanted to talk about is known as a neural net or neural network. And neural nets look something like this. So you have an input layer. This is where all your features would go. And they have all these arrows pointing to some sort of hidden layer, and then all these arrows point to some sort of output layer. So what does all of this mean? Each of these layers in here, this is something known as a neuron. Okay, so that's a neuron. In a neural net, these are all of our features that we're inputting into the neural net. So that might be x0, x1, all the way through xn, right? And these are the features that we talked about. They might be, the pregnancy, the BMI, the age, etc. And now all of these get weighted by some value. So they get multiplied by some W number that applies to that one specific category, that one specific feature. So these two get multiplied. And the sum of all of these goes into that neuron. Okay, so basically I'm taking W0 times X0, and then I'm adding X1 times W1, and then I'm adding, X2 times W2, etc., all the way to Xn times Wn. And that's getting input into the neuron. Now I'm also adding this bias term, which just means, okay, I might want to shift this by a little bit. So I might add 5, or I might add 0.1, or I might subtract 100, I don't know. But we're gonna add this bias term. And the output of all of these things, so the sum of this, and this, go into something known as an activation function, okay? And then after applying this activation function, we get an output. And this is what a neuron would look like. Now a whole network of them would look something like this. So I kind of glossed over this activation function. What exactly is that? This is how a neural net looks like. If we have all our inputs here, and let's say all of these arrows represent some sort of addition, right? Then what's going on is we're just adding a bunch of times, right? We're adding some sort of weight times these input layer a bunch of times. And then if we were to go back and factor that all out, then this entire neural net is just a linear combination of these input layers. Which, I don't know about you, but that just seems kind of useless, right? Because we could literally just write that out in a formula. Why would we need to set up this entire neural network? We wouldn't. So the activation function is introduced, right? So without an activation function, this just becomes a linear model. An activation function might look something like this. And as you can tell, these are not linear. And the reason why we introduce these is so that our entire model doesn't collapse on itself and become a linear model. So over here, this is something known as a sigmoid function. It runs between 0 and 1. Tanh runs between -1 all the way to 1. And this is ReLU, which anything less than 0 is 0, and then anything greater than 0 is linear. So with these activation functions, every single output of a neuron is no longer just the linear combination of these. It's some sort of altered linear state, which means that the input into the next neuron is, it doesn't collapse on itself. It doesn't become linear because we've introduced all of these non-linearities. So this is the training set, the model, the loss, right? And then we do this thing called training where we have to feed the loss back into the model and make certain adjustments to the model to improve this predicted output. Let's talk a little bit about the training. What exactly goes on during that step? Let's go back and take a look at our L2 loss function. This is what our L2 loss function looks like. It's a quadratic formula, right? Well, up here, the error is really, 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 really large. And our goal is to get somewhere down here where the loss is decreased, right? Because that means that our predicted value is closer to our true value. So that means that we want to go this way, okay? And thanks to a lot of properties of math, something that we can do is called gradient descent in order to follow this slope down this way. This quadratic it has different slopes with respect to some value. Okay, so the loss with respect to some weight W0 versus W1 versus Wn, they might all be different, right? So some way that I kind of think about it is, to what extent is this value contributing to our loss? And we can actually figure that out through some calculus, which we're not going to touch up on in this specific course, but if you want to learn more about neural nets, you should probably also learn some calculus and figure out what exactly backpropagation is doing in order to actually calculate, how much do we have to backstep by. So the thing is here, you might notice that this follows this curve at all of these different points. And the closer we get to the bottom, the smaller this step becomes. Now stick with me here. So my new value, this is what we call a weight update. I'm gonna take W0 and I'm gonna set some new value for W0. And what I'm gonna set for that is the old value of W0 plus some factor, which I'll just call alpha for now, times whatever this arrow is. So that's basically saying, okay, take our old W0, our old weight, and just decrease it this way. So I guess increase it in this direction, right? Like take a step in this direction, but this alpha here is telling us, okay, don't take a huge step, right? Just in case we're wrong, take a small step. Take a small step in that direction, see if we get any closer. And for those of you who, do want to look more into the mathematics of things, the reason why I use a plus here is because this here is the negative gradient, right? If this were if you were to use the actual gradient, this should be a minus. Now this alpha is something that we call the learning rate, okay? And that adjusts how quickly we're taking steps, and that might, tell that will ultimately control how long it takes for our neural net to converge, or sometimes if you set it too high, it might even diverge. But with all of these weights, so here I have W0, W1, and then Wn, we make the same update to all of them after we calculate the loss, the gradient of the loss with respect to that weight. So that's how backpropagation works. And that is everything that's going on here. After we calculate the loss, we're calculating gradients, making adjustments in the model. So we're setting all the weights to something adjusted slightly. And then we're saying, okay, let's take the training set and run it through the model again and go through this loop all over again. So for machine learning, we already have seen some libraries that we use, right? We've already seen sklearn. But when we start going into neural networks, this is kind of what we're trying to program. And it's not very fun to try to program this from scratch, because not only will we probably have a lot of bugs, but also it's probably not going to be fast enough, right? Wouldn't it be great if there are just some, full-time professionals that are dedicated to solving this problem, and they could literally just give us their code that's already running really fast? Well, the answer is yes, that exists. And that's why we use TensorFlow. So TensorFlow makes it really easy to define these models, but we also have enough control over what exactly we're feeding into this model. So for example, this line here is basically saying, okay, let's create a sequential neural net. So sequential is just, what we've seen here. It just goes one layer to the next. And a dense layer means that all of them are interconnected. So here, this is interconnected with all of these nodes, and this one's all of these, and then this one gets connected to all of the next ones, and so on. So we're gonna create 16 dense nodes with ReLU activation functions, and then we're gonna create another layer of 16 dense nodes with ReLU activation. And then our output layer is going to be just one node, okay? And that's how easy it is to define something in TensorFlow. So TensorFlow is an open source library that helps you develop and train your ML models. Let's implement this for a neural net. So we're using a neural net for classification now. So our neural net model, we are going to use TensorFlow, and I don't think I imported that up here. So we are going to import that down here. So I'm going to import TensorFlow as TF and enter. Cool. So my neural net model is going to be, I'm going to use this. So essentially this is saying layer all these things that I'm about to pass in. So yeah, layer them, linear stack of layers, layer them as a model. And what that means, nope, not that. So what that means is I can pass in some sort of layer, and I'm just going to use a dense layer. Dot dense. And let's say we have 32 units. Okay. I will also set the activation as ReLU. And at first we have to specify the input shape. So here we have 10, comma. All right. All right, so that's our first layer. Now our next layer, I'm just gonna have another a dense layer of 32 units, all using ReLU. And that's it. So for the final layer, this is just going to be my output layer. It's going to just be one node, and the activation is going to be sigmoid. So if you recall from our logistic regression, what happened there was when we had a sigmoid, it looked something like this, right? So by creating a sigmoid activation on our last layer, we're essentially projecting our predictions to be 0 or 1, just like in logistic regression. And that's going to help us, you know, we can just round to 0 or 1 and classify that way. So this is my neural net model, and I'm going to compile this. So in TensorFlow, we have to compile it. It's really cool because I can just literally pass in what type of optimizer I want and it'll do it. So here, if I go to the optimizers, I'm actually going to use Atom. And you'll see that, you know, the learning rate is 0.001. So I'm just going to use that default. So 0.001. And my loss is going to be binary cross entropy. And the metrics that I'm also going to include on here. So it already will consider loss, but I'm also going to tack on accuracy so we can actually see that in a plot later on. All right, so I'm going to run this. And one thing that I'm going to also do is I'm going to define these plot definitions. So I'm actually copying and pasting this. I got these from TensorFlow. So if you go on to some TensorFlow tutorial, they actually have this like defined. And that's exactly what I'm doing here. So I'm actually going to move this cell up, run that. So we're basically plotting the loss over all the different epochs. Epochs means like training cycles. And we're gonna plot the accuracy over all of the epochs. All right, so we have our model. And now all that's left is let's train it, okay? So I'm going to say history. So TensorFlow is great because it keeps track of the history of the training, which is why we can go and plot it later on. Now I'm going to set that equal to this neural net model and fit that with x train, y train. I'm going to make the number of epochs equal to, let's just use 100 for now. And the batch size, I'm going to set equal to, let's say 32. All right. And the validation split. So what the validation split does, if it's down here somewhere. Okay, so yeah, this validation split is just the fraction of the training data to be used as validation data. So essentially every single epoch, what's going on is TensorFlow saying leave certain, if this is 0.2, then leave 20% out, and we're going to test how the model performs on that 20% that we've left out. Okay, so it's basically like our validation data set, but TensorFlow does it on our training data set during the training. So we have now a measure outside of just our validation data set to see, you know, what's going on. So validation split, I'm going to make that 0.2. And we can run this. So if I run that, all right, and I'm actually going to set verbose equal to 0, which means, okay, don't print anything, because printing something for 100 epochs might get kind of annoying. So I'm just gonna let it run, let it train, and then we'll see what happens. Cool, so it finished training. And now what I can do is, because, you know, I've already defined these two functions, I can go ahead and I can plot the loss, plot loss of that history. And I can also plot the accuracy throughout the training. So this is a little bit-ish what we're looking for. We definitely are looking for a steadily decreasing loss and an increasing accuracy. So here we do see that, you know, our validation accuracy improves from around 0.77 or something all the way up to somewhere around maybe 0.81. And our loss is decreasing, so this is good. It is expected that the validation loss and accuracy is performing worse than the training loss or accuracy, and that's because our model is training on that data. So it's adapting to that data, whereas the validation stuff is, you know, stuff that it hasn't seen yet. So that's why. So in machine learning, as we saw above, we could change a bunch of the parameters, right? Like I could change this to 64. So now it'd be a row of 64 nodes, and then 32, and then 1. So I can change some of these parameters. And a lot of machine learning is trying to find, hey, what do we set these hyperparameters to? So what I'm actually going to do is I'm going to rewrite this so that we can do something, what's known as a grid search. So we can search through an entire space of, hey, what happens if, you know, we have 64 nodes and 64 nodes, or 16 nodes and 16 nodes, and so on. And then on top of all that, we can, you know, we can change this learning rate. We can change how many epochs, we can change, you know, the batch size. All these things might affect our training. And just for kicks, I'm also going to add what's known as a dropout layer in here. And what dropout is doing is saying, hey, randomly choose at this rate certain nodes and don't train them in, you know, a certain iteration. So this helps prevent overfitting. Okay, so I'm actually going to define this as a function called train model. We're going to pass in x train, y train, the number of nodes, the dropout, you know, the probability that we just talked about, learning rate. So I'm actually going to say LR, batch size, and we can also pass in the number of epochs, right? I mentioned that as a parameter. So indent this so it goes under here. And with these two, I'm going to set this equal to number of nodes. And now with the two dropout layers, I'm going to set dropout prob. So now, you know, the probability of turning off a node during the training is equal to dropout prob. And I'm going to keep the output layer the same. Now I'm compiling it, but this here is now going to be my learning rate. And I still want binary cross entropy and accuracy. We are actually going to train our model inside of this function. But here we can do the epochs equals epochs, and this is equal to whatever, you know, we're passing in. X train, Y train belong right here. Okay, so those are getting passed in as well. And finally at the end, I'm going to return this model and the history of that model. Okay. So now what I'll do is let's just go through all of these. So let's keep epochs at 100. And now what I can do is I can say, hey, for a number of nodes in, let's do 16, 32, and 64 to see what happens. For the different dropout probabilities in, 0 would be nothing. Let's use 0.2 also to see what happens. For the learning rate in 0.005, 0.001, and maybe we want to throw on 0.1 in there as well. And then for the batch size, let's do 16, 32, 64 as well. Actually, and let's also throw in 128. Actually, let's get rid of 16. Sorry. Let's throw in 128 in there. That should be 0, 1. I'm going to record the model in history using this train model here. So we're going to do X train, Y train. The number of nodes is going to be, the number of nodes that we've defined here. Dropout, prob, LR, batch size, and epochs. Okay. And then now we have both the model and the history. And what I'm going to do is, again, I want to plot the loss for the history. I'm also going to plot the accuracy. Probably should have done them side by side. That probably would have been easier. Okay, so what I'm going to do is split this up, and that will be subplots. So now this is just saying, okay, I want 1 row and 2 columns in that row for my plots. Okay, so I'm going to plot on my axis 1 the loss. I don't actually know this is gonna work. Okay, we don't care about the grid. Yeah, let's keep the grid. And then now on my other, so now on here, I'm going to plot all the accuracies on the second plot. I might have to debug this a bit, but we should be able to get rid of that. If we run this, we already have history saved as a variable in here. So if I just run it on this, okay, it has no attribute X label. Oh, I think it's because it's like set X label or something. Okay, yeah, so it's set instead of just X label, Y label. So let's see if that works. All right, cool. And let's actually make this a bit larger. Okay, so we can actually change the figure size, and I'm gonna set, let's see what happens if I set that to, oh, that's not the way I wanted it. Okay, so that looks reasonable. And that's just going to be my plot history function. So now I can plot them side by side. Here I'm going to plot the history. And what I'm actually going to do is so here first I'm going to print out all these parameters. So I'm going to print out, use the F string to print out all of this stuff. So here I'm printing out how many nodes, the dropout probability, the learning rate, and we already know how many epochs, so I'm not even going to bother with that. So once we plot this, let's actually also figure out what the validation loss is on our validation set that we have, that we created all the way back up here. All right, so remember we created 3 data sets. Let's call our model and evaluate what the validation data, what the validation data set's loss would be. And I actually want to record, let's say I want to record whatever model has the least validation loss. So first I'm going to initialize that to infinity so that, you know, any model will beat that score. So if I do float infinity, that will set that to infinity. And maybe I'll keep track of the parameters. Actually, it doesn't really matter. I'm just going to keep track of the model. And I'm going to set that to none. So now down here, if the validation loss is ever less than the least validation loss, then I am going to simply come down here and say, hey, this validation, or this least validation loss is now equal to the validation loss. And the least loss model is whatever this model is that just earned that validation loss. Okay? So we are actually just going to let this run for a while, and then we're going to get our least loss model after that. So let's just run. All right, and now we wait. All right, so we've finally finished training, and you'll notice that, okay, down here, the loss actually gets to like 0.29. The accuracy is around 88%, which is pretty good. So you might be wondering, okay, why is this accuracy and this, like, these are both the validation. So this accuracy here is on the validation data set that we've defined at the beginning, right? And this one here, this is actually taking 20% of our training set every time during the training and saying, okay, how much of it do I get right now? You know, after this one step where I didn't train with any of that. So they're slightly different. And actually I realized later on that I probably what I should have done is over here when we were defining the model fit, instead of the validation split, you can define the validation data and you can pass in the validation data. I don't know if this is the proper syntax, but that's probably what I should have done. But instead, you know, we'll just stick with what we have here. So you'll see at the end, you know, with the 64 nodes, it seems like this is our best performance. 64 nodes with a dropout of 0.2, a learning rate of 0.001, and a batch size of 64. And it does seem like, yes, the validation, you know, the fake validation, but the validation loss is decreasing, and then the accuracy is increasing, which is a good sign. Okay, so finally, what I'm going to do is I'm actually just going to predict. So I'm going to take this model, which we've called our least loss model. I'm going to take this model and I'm going to predict X test on that. And you'll see that it gives me some values that are really close to 0 and some that are really close to 1. And that's because we have a sigmoid output. So if I do this, and what I can do is I can cast them. So I'm going to say anything that's greater than 0.5, set that to 1. So if I think, what happens if I do this? Oh, okay, so I have to cast that as type int. So now you'll see that it's 1s and 0s. And I'm actually going to transform this into a column as well. So here I'm going to, oh, oops. I didn't mean to do that. Okay, no, I wanted to just reshape it to that. So now it's one-dimensional, okay? And using that, we can actually just rerun the classification report based on this neural net output. And you'll see that, okay, the F1s, or the accuracy gives us 87%. So it seems like what happened here is the precision on class 0, so the hadrons, has increased a bit, but the recall decreased. But the F1 score is still at a good 0.81. And for the other class, it looked like the precision decreased a bit, the recall increased for an overall F1 score that's also been increased. I think I interpreted that properly. I mean, we went through all this work and we got a model that performs actually very, very similarly to the SVM model that we had earlier. And the whole point of this exercise was to demonstrate, okay, these are how you can define your models, but it's also to say, hey, maybe, neural nets are very, very powerful, as you can tell, but sometimes, an SVM or some other model might actually be more appropriate. But in this case, I guess it didn't really matter which one we used at the end. An 87% accuracy score is still pretty good. So yeah, let's now move on to regression. We just saw a bunch of different classification models. Now let's shift gears into regression, the other type of supervised learning. If we look at this plot over here, we see a bunch of scattered data points. And here we have our X value for those data points, and then we have the corresponding Y value, which is now our label. And when we look at this plot, well, our goal in regression is to find the line of best fit that best models this data. Essentially, we're trying to, let's say we're given some new value of X that we don't have in our sample. We're trying to say, okay, what would my prediction for Y be for that given X value? So that, might be somewhere around there. I don't know. But remember in regression that, given certain features, we're trying to predict some continuous numerical value for Y. In linear regression, we want to take our data and fit a linear model to this data. So in this case, our linear model might look something along the lines of here, right? So this here would be considered as maybe our line of best fit. And this line is modeled by the equation, I'm going to write it down here, y equals b0 plus b1x. Now b0 just means it's this y-intercept, so if we extend this y down here, this value here is b0, and then b1 defines the slope of this line, okay? All right, so that's the formula for linear regression. And how exactly do we come up with that formula? What are we trying to do with this linear regression? We could just eyeball where should the line be, but humans are not very good at eyeballing certain things like that. I mean, we can get close, but a computer is better at giving us a precise value for B0 and B1. Well, let's introduce the concept of something known as a residual. Okay, so residual. You might also hear this being called the error. And what that means is, let's take some data point in our data set and we're going to evaluate how far off is our prediction from a data point that we already have. So this here is our Y. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8. So this is Y8, let's call it. You'll see that I use this yi in order to represent, hey, just one of these points, okay? So this here is y8, and this here would be the prediction, oops. This here would be the prediction for y8, which I've labeled with this hat, okay? If it has a hat on it, that means, hey, this is my guess. This is my prediction for, this specific value of x, okay? Now, the residual would be this distance here between y8 and y hat 8. So y8 minus y hat 8, all right, because that would give us this here. And I'm just going to take the absolute value of this, because what if it's below the line, right? Then you would get a negative value, but distance can't be negative, so we're just going to put a little hat, or we're going to put a little absolute value around this quantity, and that gives us the residual or the error. So let me rewrite that. And, you know, to generalize to all the points, I'm going to say the residual can be calculated as yi minus y hat of I, okay? So this just means the distance between some given point and its prediction, its corresponding prediction on the line. So now with this residual, this line of best fit is generally trying to decrease these residuals as much as possible. So now that we have some value for the error, our line of best fit is trying to decrease the error as much as possible for all of the different data points. And that might mean, you know, minimizing the sum of all the residuals. So this here, this is the sum symbol. And if I just stick the residual calculation in there, it looks something like that, right? And I'm just gonna say, okay, for all of the i's in our data set, so for all the different points, we're gonna sum up all the residuals, and I'm going to try to decrease that with my line of best fit. So I'm gonna find the B0 and B1, which gives me the lowest value of this, okay? Now, in other, you know, sometimes in different circumstances, we might attach a squared to that. So we're trying to decrease the sum of the squared residuals. And what that does is it just, you know, it adds a higher penalty for how far off we are from, you know, points that are further off. So that is linear regression. We're trying to find this equation, some line of best fit that will help us decrease this measure of error with respect to all the data points that we have in our data set and try to come up with the best prediction for all of them. This is known as simple linear regression. And basically that means, you know, our equation looks something like this. Now, there's also multiple linear regression, which just means that, hey, if we have more than one value for x, so like think of our feature vectors, we have multiple values in our x vector, then our predictor might look something more like this. Actually, I'm just gonna say etc. plus bn xn. So now I'm coming up with some coefficient for all of the different x values that I have in my vector. Now, you guys might have noticed that I have some assumptions over here, and you might be asking, okay, Kylie, what in the world do these assumptions mean? So let's go over them. The first one is linearity. And what that means is, let's say I have a data set, okay? Linearity just means, okay, does my data follow a linear pattern? Does y increase as x increases, or does y decrease as x increases? So if y increases or decreases at a constant rate as x increases, then you're probably looking at something linear. So what's an example of a nonlinear data set? Let's say I had data that might look something like that, okay? So now just visually judging this, you might say, okay, it seems like the line of best fit might actually be some curve like this, right? And in this case, we don't satisfy that linearity assumption anymore. So with linearity, we basically just want our data set to follow some sort of linear trajectory. And independence, our second assumption, just means this point over here, it should have no influence on this point over here, or this point over here, or this point over here. So in other words, all the points, all the samples in our data set should be independent, okay? They should not rely on one another. They should not affect one another. Okay, now, normality and homoscedasticity, those are concepts which use this residual, okay? So if I have a plot that looks something like this, and my line of best fit is somewhere here, maybe it's something like that. In order to look at these normality and homoscedasticity assumptions, let's look at the residual plot, okay? And what that means is I'm going to keep my same x-axis, but instead of plotting now where they are relative to this y, I'm going to plot these errors. So now I'm going to plot y minus y hat, like this, okay? And now, you know, this one is slightly positive, so it might be here. This one down here is negative, it might be here. So our residual plot, it's literally just a plot of how, you know, the values are distributed around our line of best fit. So it looks like it might, you know, look something like this, okay? So this might be our residual plot. And what normality means, so our assumptions are normality and homoscedasticity. I might have butchered that spelling, I don't really know. But what normality is saying, okay, these residuals should be normally distributed, okay, around this line of best fit. It should follow a normal distribution. And now what homoscedasticity says, okay, our variance of these points should remain constant throughout. So this spread here should be approximately the same as this spread over here. Now, what's an example of where, you know, homoscedasticity is not held? Well, let's say that our original plot actually looks something like this. Okay, so now if we looked at the residuals for that, it might look something like that. And now if we look at this spread of the points, it decreases, right? So now the spread is not constant, which means that homoscedasticity, this assumption would not be fulfilled, and it might not be appropriate to use linear regression. So that's just linear regression. Basically, we have a bunch of data points. We want to predict some y value for those. And we're trying to come up with this line of best fit that best describes, hey, given some value x, what would be my best guess of what y is? So let's move on to how do we evaluate a linear regression model? So the first measure that I'm going to talk about is known as mean absolute error, or MAE for short, okay? And mean absolute error is basically saying, all right, let's take all the errors, so all these residuals that we talked about, let's sum up the distance for all of them and then take the average, and then that can describe, you know, how far off are we? So the mathematical formula for that would be, okay, let's take all the residuals. All right, so this is the distance. Actually, let me redraw a plot down here. So suppose I have a data set look like this, and here are all of my data points, right? And now let's say my line looks something like that. So my mean absolute error would be summing up all of these values. This was a mistake. So summing up all of these and then dividing by how many data points I have. So what would be all the residuals? It would be yi, right? So every single point minus y hat I, so the prediction for that on here. And then we're going to sum over all of the different i's in our data set, right? So and then we divide by the number of points we have. So actually I'm going to rewrite this to make it a little clearer. So I is equal to whatever the first data point is all the way through the nth data point. And then we divide it by n, which is how many points there are. Okay, so this is our measure of MAE. And this is basically telling us, okay, on average, this is the distance between our predicted value and the actual value in our training set. Okay? And MAE is good because it allows us to, when we get this value here, we can literally directly compare it to whatever units the Y value is in. So let's say Y is, we're talking, the prediction of the price of a house, right? In dollars. Once we calculate the MAE, we can literally say, oh, the average, price, the average, how much we're off by is literally this many dollars. Okay? So that's the mean absolute error. An evaluation technique that's also closely related to that is called the mean squared error. And this is MSE for short. Okay? Now, if I take this plot again and I duplicate it and move it down here, well, the gist of mean squared error is kind of the same, but instead of the absolute value, we're going to square. So now the MSE is something along the lines of, okay, let's sum up something, right? So we're going to sum up all of our errors. So now I'm going to do yi minus y hat I, but instead of absolute valuing them, I'm going to square them all. And then I'm going to divide by n in order to find the mean. So basically now I'm taking all of these different values and I'm squaring them first before I add them to one another. And then I divide by n. And the reason why we like using mean squared error is that it helps us punish large errors in the prediction. And later on, MSE might be important because of differentiability, right? So a quadratic equation is differentiable. If you're familiar with calculus, a quadratic equation is differentiable, whereas the absolute value function is not totally differentiable everywhere. But if you don't understand that, don't worry about it. You won't really need it right now. And now one downside of mean squared error is that once I calculate the mean squared error over here, and I go back over to y and I want to compare the values, well, it gets a little bit trickier to do that because now my mean squared error is in terms of y squared, right? This is now squared, so instead of just dollars, how many dollars off am I? I'm talking how many dollars squared off am I? And that, to humans, it doesn't really make that much sense, which is why we have created something known as the root mean square error. And I'm just going to copy this diagram over here because it's very, very similar to mean squared error, except now we take a big squared root. Okay, so this is RMSE, and we take the square root of that mean squared error. And so now the term in which, we're defining our error is now in terms of that $ symbol again. So that's a pro of root mean squared error, is that now we can say, okay, our error according to this metric is this many $ off from our predictor. Okay, so it's in the same unit, which is one of the pros of root mean squared error. And now finally, there is the coefficient of determination, or R squared. And this is the formula for R squared. So R squared is equal to 1 minus RSS over TSS. Okay, so what does that mean? Basically, RSS stands for the sum of the squared residuals. So maybe it should be SSR instead, but RSS, sum of the squared residuals. And this is equal to, if I take the sum of all the values and I take yi minus y hat I, and square that, that is my RSS, right? It's a sum of the squared residuals. Now TSS, let me actually use a different color for that. So TSS is the total sum of squares. And what that means is that instead of being with respect to this prediction, we are instead going to take each y value and just subtract the mean of all the y values and square that. Okay, so if I drew this out, and if this were my, actually let's use a different color. Let's use green. If this were my predictor, so RSS is giving me this measure here, right? It's giving me some estimate of how far off we are from our regressor that we predicted. Actually, I'm gonna use red for that. Well, TSS, on the other hand, is saying, okay, how far off are these values from the mean? So if we literally didn't do any calculations for the line of best fit, if we just took all the y values and averaged all of them and said, hey, this is the average value for every single x value, I'm just gonna predict that average value instead, then it's asking, okay, how far off are all these points from that line? Okay, and remember that this square means that we're punishing larger errors, right? So even if they look somewhat close in terms of distance, the further a few data points are, then the larger our total sum of squares is going to be. Sorry, that was my dog. So the total sum of squares is taking all of these values and saying, okay, what is the sum of squares? If I didn't do any regressor and I literally just calculated the average of all the y values in my data set, and for every single x value, I'm just gonna predict that average. Which means that, okay, like that means that maybe y and x aren't associated with each other at all. Like the best thing that I can do for any new x value is just predict, hey, this is the average of my data set. And this total sum of squares is saying, okay, well, with respect to that average, what is our error, right? So up here, this sum of the squared residuals, this is telling us what is our error with respect to this line of best fit, while our total sum of squares is saying what is the error with respect to, you know, just the average y value. And if our line of best fit is a better fit than this total sum of squares, that means that, you know, this numerator, is going to be smaller than this denominator, right? And if our errors in our line of best fit are much smaller, then that means that this ratio of the RSS over TSS is going to be very small, which means that R squared is going to go towards 1. And now when R squared is towards 1, that means that that's usually a sign that we have a good predictor. It's one of the signs, not the only one. So over here, I also have, you know, that there's this adjusted R squared. And what that does, it just adjusts for the number of terms. So x1, x2, x3, etc. It adjusts for how many extra terms we add, because usually when we, you know, add an extra term, the R squared value will increase because that'll help us predict y some more. But the value for the adjusted R squared increases if the new term actually improves this model fit more than expected, you know, by chance. So that's what adjusted R squared is. I'm not, you know, it's out of the scope of this one specific course. And now that's linear regression. Basically, I've covered the concept of residuals or errors and, you know, how do we use that in order to find the line of best fit? And, you know, our computer can do all the calculations for us, which is nice. But behind the scenes, it's trying to minimize that error, right? And then we've gone through all the different ways of actually evaluating a linear regression model and the pros and cons of each one. So now let's look at an example. So we're still on supervised learning, but now we're just going to talk about regression. So what happens when you don't just want to predict, type 1, 2, 3? What happens if you actually want to predict a certain value? So again, I'm on the UCI machine learning repository, and here I found this data set about bike sharing in Seoul, South Korea. So this data set is predicting rental bike count. And here it's the count of bikes rented at each hour. So what we're going to do, again, you're going to go into the data folder and you're going to download this CSV file. And we're going to move over to Colab again. And here I'm going to name this FCC bikes and regression. I don't remember what I called the last one, but yeah, FCC bikes regression. Now I'm going to import a bunch of the same things that I did earlier. And I'm going to also continue to import the oversampler and the standard scalar. And then I'm actually also just going to let you guys know that I have a few more things I want to import. So this is a library that lets us copy things. Seaborn is a wrapper over Matplotlib, so it also allows us to plot certain things. And then just letting you know that we're also going to be using TensorFlow. Okay, so one more thing that we're also going to be using, we're going to use the sklearn linear model library. And actually, let me make my screen a little bit bigger. So yeah, awesome. Run this and that'll import all the things that we need. So again, I'm just going to, give some credit to where we got this data set. So let me copy and paste this UCI thing. And I will also give credit to this here. Okay, cool. All right, cool. So this is our data set. And again, it tells us all the different attributes that we have right here. So I'm actually going to go ahead and paste this in here. Feel free to copy and paste this if you want me to read it out loud so you can type it. It's bike count, hour, temp, humidity, wind, visibility, dew point temp, radiation, rain, snow, and functional, whatever that means. Okay, so I'm going to come over here and import my data by dragging and dropping. All right. Now, one thing that you guys might actually need to do is you might actually have to open up this CSV because there were at first a few like forbidden characters in mine at least. So you might have to get rid of, like, I think there was a degree here, but my computer wasn't recognizing it, so I got rid of that. So you might have to go through and get rid of some of those labels that are incorrect. I'm gonna do this, okay. But after we've done that, we've imported in here, I'm going to create a data frame from that. So, all right, so now what I can do is I can read that CSV file and I can get the data into here. So bike data dot CSV. Okay, so now if I call data.head, you'll see that I have all the various labels, right? And then I have the data in there. So I'm going to, from here, I'm actually going to get rid of some of these columns that, I don't really care about. So here I'm going to, when I type this in, I'm going to drop maybe the date, whether or not it's a holiday, and the various seasons. So I'm just not gonna care about these things. Axis equals 1 means drop it from the columns. So now you'll see that, okay, we still have, I guess you don't really notice it, but if I set the data frames columns equal to data set calls, and I look at, the first 5 things, then you'll see that this is now our data set. It's a lot easier to read. So another thing is I'm actually going to df functional, and we're going to create this. So remember that our computers are not very good at language. We want it to be in zeros and ones. So here I will convert that. Well, if this is equal to yes, then that gets mapped as 1. So then set type integer. All right, great, cool. So the thing is, right now, these byte counts are for whatever hour. So to make this example simpler, I'm just going to index on an hour, and I'm gonna say, okay, we're only going to use that specific hour. So here, let's say, so this data frame is only gonna be data frame where the hour, let's say it equals 12. Okay, so it's noon. All right. So now you'll see that all the hours are equal to 12, and I'm actually going to now drop that column. Hour axis equals 1. All right, so if we run this cell, okay, so now we got rid of the hour in here, and we just have the byte count, the temperature, humidity, wind, visibility, and yada, yada, yada. All right. So what I want to do is I'm going to actually plot all of these. So for in all the columns, so the range length of whatever this data frame is and all the columns, because I don't have byte count as, actually it's my first thing. So what I'm going to do is say for a label in data frame columns, everything after the first thing. So that would give me the temperature and onward. So these are all my features, right? I'm going to just scatter. So I want to see how that label, how that specific data, how that affects the byte count. So I'm going to plot the byte count on the y-axis, and I'm going to plot, whatever the specific label is on the x-axis. And I'm going to title this, whatever the label is, and, make my Y label the byte count at noon, and the X label as just the label. Okay, now I guess we don't even need the legend. So just show that plot. All right. So it seems like functional is not really, doesn't really give us any utility. So then snow, rain, seems like this radiation, is fairly linear. Dew point temperature, visibility, wind doesn't really seem like it does much. Humidity, kind of maybe like an inverse relationship. But the temperature definitely looks like there's a relationship between that and the number of bikes, right? So what I'm actually going to do is I'm going to drop some of the ones that don't seem like they really matter. So maybe wind, visibility. Yeah, so I'm going to get rid of wind, visibility, and functional. So let me now data frame, and I'm going to drop wind, visibility, and functional. All right, and the axis again is the column, so that's 1. So if I look at my data set now, I have just the temperature, the humidity, the dew point temperature, radiation, rain, and snow. So again, what I want to do is I want to split this into my training, my validation, and my test data set, just as we talked before. Here, we can use the exact same thing that we just did, and we can say numpy.split and sample, the whole sample, and then create our splits of the data frame. And we're going to do that, but now set this to 8. Okay. So I don't really care about, the full grid, the full array. So I'm just gonna use an underscore for that variable, but I will get my training X and Y's. And actually, I don't have a function for getting the X and Y's. So here, I'm going to write a function to find get X, Y. And I'm going to pass in the data frame. And I'm actually going to pass in what the name of the Y label is and what specific X labels I want to look at. So here, if that's none, then I'm just not, like, I'm going to get everything from the data set. That's not the Y label. So here I'm actually going to make first a deep copy of my data frame. And that basically means I'm just copying everything over. If like X labels is none, so if not X labels, then all I'm going to do is say, all right, X is going to be whatever this data frame is. And I'm just going to take all the columns. So C for C in data frame dot columns if C does not equal the Y label. All right. And I'm going to get the values from that. But if there is the X labels, well, okay, so in order to index only one thing, so like let's say I pass in only one thing in here, then my data frame is, so let me make a case for that. So if the length of X labels is equal to 1, then what I'm going to do is just say that this is going to be X labels and add that, just that label, values, and I actually need to reshape to make this 2D. So I'm going to pass in -1, 1 there. Now, otherwise, if I have like a list of specific X labels that I want to use, then I'm actually just going to say X is equal to data frame of those X labels dot values. And that should suffice. All right, so now that's just me extracting X. And in order to get my Y, I'm going to do Y equals data frame and then pass in the Y label. And at the very end, I'm going to say data equals NP dot HStack. So I'm stacking them horizontally, one next to each other. And I'll take X and Y and return that. Oh, but this needs to be values. And I'm actually going to reshape this to make it 2D as well so that we can do this HStack. And I will return data, X, Y. So now I should be able to say, okay, get X, Y, and take that data frame and the Y label. So our Y label is byte count. And actually, so for the X label, I'm actually going to, let's just do like one dimension right now. And earlier I got rid of the plots, but we had seen that maybe, you know, the temperature dimension does really well, and we might be able to use that to predict Y. So I'm going to label this also that, you know, it's just using the temperature. And I am also going to do this again for, oh, this should be train, and this should be validation, and this should be test. Because, oh, that's val. All right. But here, this should be val, and this should be test. All right. So we run this, and now we have our training, validation, and test data sets for just the temperature. So if I look at X train temp, it's literally just the temperature. Okay, and I'm doing this first to show you simple linear regression. All right, so right now I can create a regressor. So I can say the temp regressor here, and then I'm going to, you know, make a linear regression model. And just like before, I can simply fit my X train temp, Y train temp in order to train this linear regression model. All right, and then I can also, print this regressor's coefficients and the intercept. So if I do that, okay, this is the coefficient for whatever the temperature is, and then the X intercept, okay? Or the Y intercept, sorry. All right. and I can, you know, score. So I can get the R squared score. So I can score X test and Y test temp. All right, so it's an R squared of around 0.38, which is better than 0, which would mean, hey, there's absolutely no association. But it's also not, you know, like a good. It depends on the context, but you know, the higher that number is means the higher that the two variables would be correlated, right? Which here it's all right. It just means there's maybe some association between the two. But the reason why I wanted to do this 1D was to show you, you know, if we plotted this, this is what it would look like. So if I create a scatter plot, and let's take the training. So this is our data, and then let's make it blue. And then if I also plotted, so something that I can do is say, you know, the X range that I'm gonna plot it is Lin space, and this goes from -20 to 40, this piece of data. So I'm gonna just say, let's take 100 things from there. So I'm going to plot X, and I'm going to take this like regressor and predict X with that, okay? And this label, I'm going to label that the fit, and this color, let's make this red. And let's actually set the line width, so I can change how thick that value is. Okay. Now at the very end, let's create a legend, and let's also create, you know, title, all these things that matter in some sense. So here, let's just say this would be the bikes versus the temperature, right? And the Y label would be number of bikes, and the X label would be the temperature. So I actually think that this might cause an error, yeah. So it's expecting a 2D array, so we actually have to reshape this. Let's array. Okay, there we go. So I just had to make this an array and then reshape it so it was 2D. Now we see that, all right, this increases, but again, remember those assumptions that we had about linear regression? Like this, I don't really know if this fits those assumptions, right? I just wanted to show you guys though that, like, all right, this is what a line of best fit through this data would look like. Okay. Now we can do multiple linear regression, right? So I'm going to go ahead and do that as well. Now, if I take my data set and instead of the labels, so actually what's my current data set right now? All right, so let's just use all of these except for the byte count, right? So I'm going to just say for the X labels, let's just take the data frames columns and just remove the byte count. So does that work? So if this part should be if X labels is none, and then this should work now. Oops, sorry. Okay, so I have, oh, but this here, because it's not just the temperature anymore, we should actually do this, let's say all, right? So I'm just going to quickly rerun this piece here so that we have our temperature only data set, and now we have our all data set, okay? And this regressor, I can do the same thing. So I can do the all regressor, and I'm gonna make this the linear regression, and I'm going to fit this to X train all and Y train all. Okay. All right, so let's go ahead and also score this regressor, and let's see how the R squared performs now. So if I test this on the test data set, what happens? All right, so our R squared seems to improve. It went from 0.4 to 0.52, which is a good sign. Okay. And I can't necessarily plot, every single dimension, but this is just to say, okay, this has improved, right? All right, so one cool thing that you can do with TensorFlow is you can actually do regression, but with the neural net. So here I'm going to, we already have our training data for just the temperature and just, for all the different columns. So I'm not gonna bother with splitting up the data again. I'm just gonna go ahead and start building the model. So in this linear regression model, typically, it does help if we normalize it. So that's very easy to do with TensorFlow. I can just create some normalizer layer. So I'm going to do TensorFlow Keras layers and get the normalization layer. And the input shape for that will just be 1, because let's just do it again on just the temperature. And the axis, I will make none. Now for this temp normalizer, and I should have had an equal sign there, I'm going to adapt this to X train temp and reshape this to just a single vector. So that should work, great. Now with this model, so temp neural net model, what I can do is I can do, dot keras, that's sequential. And I'm gonna pass in this normalizer layer, and then I'm gonna say, hey, just give me one single dense layer with one single unit. And what that's doing is saying, all right, well, one single node just means that it's linear. And if you don't add any sort of activation function to it, the output is also linear. So here I'm going to have TensorFlow Keras layers dot dense, and I'm just gonna have one unit. And that's going to be my model, okay? So with this model, let's compile. And for our optimizer, let's use Atom again. Atom, and we have to pass in the learning rate. So learning rate, and our learning rate, let's do 0.01. And now the loss, let's give this one 0.1. And the loss, I'm going to do mean squared error. Okay, so we run that, we've compiled it, okay, great. And just like before, we can call history, and I'm going to fit this model. So here, if I call fit, I can just fit it, and I'm going to take the X train with the temperature, but reshape it, Y train for the temperature. And I'm going to set verbose equal to 0 so that it doesn't, display stuff. I'm actually going to set epochs equal to, let's do 1000. And the validation data should be, let's pass in the validation data set here as a tuple. And I know I spelled that wrong. So let's just run this. And up here, I've copy and pasted the plot loss from our previous, but changed the Y label to MSE, because now we're dealing with mean squared error. And I'm going to plot the loss of this history after it's done. So let's just wait for this to finish training and then to plot. Okay, so this actually looks pretty good. We see that the values are converging. So now what I can do is I'm going to go back up and take this plot, and we are going to just run that plot again. So here, instead of this temperature regressor, I'm going to use the neural net regressor, this neural net model. And if I run that, I can see that, this also gives me a linear regressor. You'll notice that this fit is not entirely the same as the one up here. And that's due to the training process of this neural net. So just two different ways to try to find the best linear regressor. Okay, but here we're using backpropagation to train a neural net node, whereas in the other one, they probably are not doing that. Okay, they're probably just trying to actually compute the line of best fit. So, okay, given this, well, we can repeat the exact same exercise with our multiple linear regressions, okay? But I'm actually going to skip that part. I will leave that as an exercise to the viewer. Okay, so now what would happen if we used a neural net, a real neural net, instead of just, one single node in order to predict this? So let's start on that code. We already have our normalizer, so I'm actually going to take the same setup here, but instead of, this one dense layer, I'm going to set this equal to 32 units. And for my activation, I'm going to use ReLU. And now let's duplicate that. And for the final output, I just want one answer. So I just want one cell. And this activation is also going to be ReLU because I can't ever have less than 0 bytes. So I'm just going to set that as ReLU. I'm just going to name this the neural net model. Okay. And at the bottom, I'm going to have this neural net model. I'm going to have this neural net model. I'm going to compile. And I will actually use the same compiler here, but instead of a learning rate of 0.01, I'll use 0.001. Okay. And I'm going to train this here. So the history is this neural net model, and I'm going to fit that against x train temp, y train temp, and validation data. I'm going to set this again equal to x val temp and y val temp. Now for the verbose, I'm going to set that equal to 0. Epochs, let's do 100. And here for the batch size, actually let's just not do a batch size right now. Let's just try, let's see what happens here. And again, we can plot the loss of this history after it's done training. So let's just run this. And that's not what we're supposed to get. So what is going on? Here is sequential. We have our temperature normalizer, which I'm wondering now if we have to redo that. Okay, so we do see this decline. It's an interesting curve, but we do see it eventually. So this is our loss, which, all right, if it's decreasing, that's a good sign. And actually, what's interesting is let's plot this model again. So here instead of that, and you'll see that we actually have this like curve that looks something like this. So actually, what if I got rid of this activation? Let's train this again and see what happens. All right, so even when I got rid of that ReLU at the end, it kind of knows, hey, if it's not the best model, if we had maybe one more layer in here. These are just things that you have to play around with when you're, working with machine learning. It's like, you don't really know what the best model is going to be. For example, this also is not brilliant, but I guess it's okay. So my point is though that with a neural net, I mean, this is not brilliant, but also there's like no data down here, right? So it's kind of hard for our model to predict. In fact, we probably should have started the prediction somewhere around here. My point though is that with this neural net model, you can see that this is no longer a linear predictor, but yet we still get an estimate of the value, right? And we can repeat this exact same exercise with the multiple inputs. So here, if I now pass in all of the data, so this is my all normalizer, and I should just be able to pass in that. So let's move this to the next cell. Here, I'm going to pass in my all normalizer, and let's compile it. Yeah, those parameters look good. Great. So here with the history, when we're trying to fit this model, instead of temp, we're going to use our larger data set with all the features. And let's just train that. And of course, we want to plot the loss. Okay, so that's what our loss looks like. It's an interesting curve, but it's decreasing. So before we saw that our R-squared score was around 0.52. Well, we don't really have that with a neural net anymore. But one thing that we can measure is, hey, what is the mean squared error, right? So if I come down here and I compare the two mean squared errors, so I can predict X test all, right? So these are my predictions using that linear regressor. Well, multiple linear regressor. So these are my Y predictions linear regression. Okay. I'm actually going to do that at the bottom. So let me just copy and paste that cell and bring it down here. So now I'm going to calculate the mean squared error for both the linear regressor and the neural net. Okay, so this is my linear and this is my neural net. So if I use my neural net model and I predict X test all, I get my two, different Y predictions. And I can calculate the mean squared error, right? So if I want to get the mean squared error and I have Y prediction and Y real, I can do numpy.square, and then I would need the Y prediction minus, the real. So this is basically squaring everything. And this should be a vector. So if I just take this entire thing and take the mean of that, that should give me the MSE. So let's just try that out. And the Y real is Y test all, right? So that's my mean squared error for the linear regressor. And this is my mean squared error for the neural net. So that's interesting. I will debug this live, I guess. So my guess is that it's probably coming from this normalization layer. Because this input shape is probably just 6. And okay, so that works now. And the reason why is because like my inputs are only, for every vector, it's only a one-dimensional vector of length 6. So I should have just had 6, comma, which is a tuple of size 6 from the start. Or it's a tuple containing one element, which is just 6. Okay, so it's actually interesting that my neural net results seem like they have a larger mean squared error than my linear regressor. one thing that we can look at is we can actually plot the real versus, you know, the actual results versus what the predictions are. So if I say some axis and I use plt.axes and make these equal, then I can scatter the y, you know, the test, so what the actual values are on the x-axis and then what the predictions are on the x-axis, okay? And I can label this as the linear regression predictions. Okay, so then let me just label my axes. So the x-axis I'm going to say is the true values. The y-axis is going to be my linear regression predictions. Or actually, let's just make this predictions. And then at the end, I'm going to plot, oh, let's set some limits. Because I think that's like approximately the max number of bikes. So I'm going to set my x limit to this and my y limit to this. So here, I'm going to pass that in here too. And all right, this is what we actually get for our linear regressor. You can see that actually they align quite well. I mean, to some extent. So 2000 is probably too much. 2500, I mean. Looks like maybe like 1800 would be enough here for our limits. And I'm actually going to label something else, the neural net predictions. Let's add a legend. So you can see that our neural net, for the larger values, it seems like it's a little bit more spread out, and it seems like we tend to underestimate a little bit down here in this area. Okay. And for some reason, these are way off as well. But yeah, so we've basically used a linear regressor and a neural net. Honestly, there are some times where a neural net is more appropriate and a linear regressor is more appropriate. I think that it just comes with time and trying to figure out, you know, and just literally seeing like, hey, what works better? Like here, a multiple linear regressor might actually work better than a neural net. But for example, with the one-dimensional case, a linear regressor would never be able to see this curve, okay? I mean, I'm not saying this is a great model either, but I'm just saying like, hey, you know, sometimes it might be more appropriate to use something that's not linear. So yeah, I will leave regression at that. Okay, so we just talked about supervised learning. And in supervised learning, we have data. We have a bunch of features and for a bunch of different samples, but each of those samples has some sort of label on it, whether that's a number, a category, a class, etc. Right? We were able to use that label in order to try to predict new labels of other points that we haven't seen yet. Well, now let's move on to unsupervised learning. So with unsupervised learning, we have a bunch of unlabeled data. And what can we do with that? You know, can we learn anything from this data? So the first algorithm that we're going to discuss is known as k-means clustering. What k-means clustering is trying to do is it's trying to compute k clusters from the data. So in this example below, I have a bunch of scattered points, and you'll see that this is x0 and x1 on the two axes, which means I'm actually plotting two different features, right, of each point, but we don't know what the y label is for those points. And now, just looking at these scattered points, we can kind of see how there are different clusters in the data set, right? So, depending on what we pick for k, we might have different clusters. Let's say k equals 2. right? Then we might pick, okay, this seems like it could be one cluster, but this here is also another cluster. So those might be our two different clusters. If we have k equals 3, for example, then, okay, this seems like it could be a cluster. This seems like it could be a cluster, and maybe this could be a cluster, right? So we could have 3 different clusters in the data set. Now this k here is predefined, if I can spell that correctly, by the person who's running the model. So that would be you. All right. And let's discuss how, the computer actually goes through and computes the k clusters. So I'm going to write those steps down here. Now the first step that happens is we actually choose, the computer chooses 3 random points on this plot to be the centroids. And by centroids, I just mean the center of the clusters, okay? So 3 random points, let's say we're doing k equals 3. So we're choosing 3 random points to be the centroids of the 3 clusters. If it were 2, we'd be choosing 2 random points, okay? So maybe the 3 random points I'm choosing might be here, here, and here. All right. So we have 3 different points. And the second thing that we do is we actually calculate the distance for each point to those centroids. So between all the points and the centroid. So basically I'm saying, all right, this is this distance, this is this distance, this is this distance. All of these distances I'm computing between, not those two, between the points, not the centroids themselves. So I'm computing the distances for all of these plots to each of the centroids. Okay? And that comes with also assigning those points to the closest centroid. What do I mean by that? So let's take this point here, for example. So I'm computing this distance, and this distance. And I'm saying, okay, it seems like the red one is the closest. So I'm actually going to put this into the red centroid. So if I do that for all of these points, this one seems slightly closer to red, and this one seems slightly closer to red, right? Now for the blue, I actually wouldn't put any blue ones in here, but we would probably, actually, that first one is closer to red. And now it seems like the rest of them are probably closer to green. So let's just put all of these into green here, like that. And cool. So now we have, you know, our 2, 3 technically centroids. So there's this group here. There's this group here. And then blue is kind of just this group here. It hasn't really touched any of the points yet. So the next step, 3, that we do is we actually go and we recalculate the centroids. So we compute new centroids based on the points that we have in all the centroids. And by that, I just mean, okay, well, let's take the average of all these points, and where is that new centroid? That's probably going to be somewhere around here, right? The blue one, we don't have any points in there, so we won't touch. And then this green one, we can put that probably somewhere over here. Oops. Somewhere over here, right? So now if I erase all of the previously computed centroids, I can go and I can actually redo step 2 over here, this calculation. All right, so I'm going to go back and I'm going to iterate through everything again, and I'm going to recompute my 3 centroids. So let's see, we're going to take this red point. These are definitely all red, right? This one still looks a bit red. Now, this part, we actually start getting closer to the blues. So this one still seems closer to a blue than a green. This one as well. And I think the rest would belong to green. Okay, so now our three clusters would be this, this, and then this, right? Those are our three centroids. And so now we go back and we compute those would be the three clusters. So now we go back and we compute the three centroids. So I'm going to get rid of this, this, and this. And now where would this red be centered? Probably closer, to this point here. This blue might be closer to up here. And then this green would probably be somewhere, it's pretty similar to what we had before, but it seems like it'd be pulled down a bit. So probably somewhere around there for green. All right, and now again, we go back and we compute the distance between all the points and the centroids, and then we assign them to the closest centroid. Okay, so the reds are all here. It's very clear. Actually, let me just circle that. And this. It actually seems like this point is closer to this blue now. So the blues seem like they would be maybe, this point looks like it'd be blue. So all these look like they would be blue now. And the greens would probably be this cluster right here. So we go back, we compute the centroids. Bam. This one probably like almost here. Bam. And then the green looks like it would be probably here-ish. Okay. And now we go back and we compute the compute the clusters again. So red, still this. Blue, I would argue, is now this cluster here. And green is this cluster here. Okay, so we go and we recompute the centroids. Bam. Bam. And, bam. And now if I were to go and assign all the points to clusters again, I would get the exact same thing, right? And so that's when we know that we can stop iterating between steps 2 and 3, is when we've converged on some solution, when we've reached some stable point. And so now, because none of these points are really changing out of their clusters anymore, we can go back to the user and say, hey, these are our 3 clusters. Okay, and this process, something known as expectation maximization. This part where we're assigning the points to the closest centroid, this is our expectation step. And this part where we're computing the new centroids, this is our maximization step. Okay, so that's expectation maximization. And we use this in order to compute the centroids, assign all the points to clusters according to those centroids, and then we're recomputing all of that over again until we reach some stable point where nothing is changing anymore. All right, so that's our first example of unsupervised learning. And basically what this is doing is trying to find some structure, some pattern in the data. So if I came up with another point, might be somewhere here, I can say, oh, it looks like that's closer to, if this is A, B, C, it looks like that's closest to cluster B. And so I would probably put it in cluster B. Okay, so we can find some structure in the data based on just how the points are scattered relative to one another. Now, the second unsupervised learning technique that I'm going to discuss with you guys is something known as principal component analysis. And the point of principal component analysis is very often it's used as a dimensionality reduction technique. So let me write that down. It's used for dimensionality reduction. And what do I mean by dimensionality reduction is if I have a bunch of features like x1, x2, x3, x4, etc., can I just reduce that down to one dimension that gives me the most information about how all of these points are spread relative to one another? And that's what PCA is for. So PCA, Principal Component Analysis. Let's say I have some points in the x0 and x1 feature space. Okay, so these points might be spread, you know, something like this. Okay. So, for example, if this were something to do with housing prices, right? This here might be, x0 might be, hey, years since built, right? Since the house was built, and x1 might be square footage of the house. All right, so like years since built, I mean like right now, it's been, you know, 22 years since a house in 2000 was built. Now, principal component analysis is just saying, all right, let's say we want to build a model, or let's say we want to, you know, display something about our data, but we don't have two axes to show it on. How do we display, you know, how do we demonstrate that this point is a further away from this point than this point? And we can do that using principal component analysis. So take what you know about linear regression and just forget about it for a second. Otherwise, you might get confused. PCA is a way of trying to find direction in the space with the largest variance. So this principal component, what that means is basically the component. So some direction in this space with the largest variance, okay? It tells us the most about our data set without the two different dimensions. Like, let's say we have these two different dimensions and somebody's telling us, hey, you only get one dimension in order to show your data set. What dimension? Like, what do? We want to project our data onto a single dimension. All right. So that, in this case, might be a dimension that looks something like this. And you might say, okay, we're not going to talk about linear regression, okay? We don't have a y value. So in linear regression, this would be y. This is not y, okay? We don't have a label for that. Instead, what we're doing is we're taking the right angle projection. So all of these that's not very visible, but take this right angle projection onto this line. And what PCA is doing is saying, okay, map all of these points onto this one-dimensional space. So the transformed data set would be here. This one's on the data set, or on the line, so we just put that there. But now this would be our new one-dimensional data set. Okay, it's not our prediction or anything. This is our new data set. If somebody came to us and said, you only get one dimension, you only get one number to represent each of these 2D points, what number would you give me? This would be the number that we gave. Okay, in this direction, this is where our points are the most spread out, right? If I took this plot, and let me actually duplicate this so I don't have to rewrite anything. Or so I don't have to erase and then redraw anything. Let me get rid of some of this stuff. And I just got rid of a point there too, so let me draw that back. All right. So if this were my original data point, what if I had taken, you know, this to be the PCA dimension. Okay, well, I then would have points that, let me actually do that in a different color. So if I were to draw a right angle to this for every point, my points would look something like this. And so just intuitively looking at these two different plots, this top one and this one, we can see that the points are squished a little bit closer together, right? Which means that the variance, that's not the space with the largest variance. The thing about the largest variance is that this will give us the most discrimination between all of these points. The larger the variance, the further spread out these points will likely be. Now, and so that's the dimension that we should project it on. A different way to actually look at that, like what is the dimension with the largest variance? It's actually, it also happens to be the dimension that decreases, that minimizes the residuals. So if we take all the points and we take the residual from that, the XY residual. So in linear regression, we were looking only at this residual, the differences between the predictions, right? Between Y and Y hat. It's not that. Here in principal component analysis, we're taking the difference from our current point in two-dimensional space and then its projected point. Okay, so we're taking that dimension and we're saying, all right, how much distance is there between that projection residual? And we're trying to minimize that for all of these points. So that actually equates to this largest variance dimension. This dimension here, the PCA dimension, you can either look at it as minimize, let me get rid of this, the projection residuals, so that's the stuff in orange, or 2, maximizing the variance between the points. Okay, and we're not really going to talk about the method that we need in order to calculate out the principal components, or like what that projection would be, because you will need to understand linear algebra for that, especially eigenvectors and eigenvalues, which I'm not going to cover in this class. But that's how you would find the principal components, okay? Now, with this two-dimensional data set here, this one-dimensional data set, we started from a 2D data set and we now boil it down to one dimension. Well, we can go and take that dimension and we can do other things with it, right? We can, like, if there were a Y label, then we can now show X versus Y rather than X0 and X1 in different plots with that Y. Now we can just say, oh, this is a principal component and we're going to plot that with the Y. Or, for example, if there were 100 different dimensions and you only wanted to take 5 of them, well, you could go and you could find the top 5 PCA dimensions, and that might be a lot more useful to you than 100 different feature vector values, right? So that's principal component analysis. Again, we're taking, certain data that's unlabeled and we're trying to make some sort of estimation, like some guess about its structure from that original data set. If we wanted to take, a 3D thing, so like a sphere, but we only have a 2D surface to draw it on, well, what's the best approximation that we can make? Oh, it's a circle, right? PCA is kind of the same thing. It's saying if we have something with all these different dimensions, but we can't show all of them, how do we boil it down to just one dimension? How do we extract the most information from that multiple dimensions? And that is exactly, either you minimize the projection residuals or you maximize the variance. And that is PCA. So we'll go through an example of that. Now, finally, let's move on to implementing the unsupervised learning part of this class. Here, again, I'm on the UCI machine learning repository, and I have a seeds data set where, you know, I have a bunch of kernels that belong to 3 different types of wheat. So there's Kama, Rosa, and Canadian. And the different features that we have access to are, you know, geometric parameters of those wheat kernels. So the area, perimeter, compactness, length, width, asymmetry, and the length of the kernel groove. Okay, so all of these are real values, which is easy to work with. And what we're going to do is we're going to try to predict, or I guess we're going to try to cluster the different varieties of the wheat. So let's get started. I have a Colab notebook open again. Oh, you're gonna have to, you know, go to the data folder, download this, and let's get started. So the first thing to do is to import our seeds data set into our Colab notebook. So I've done that here. Okay, and then we're going to import all the classics again. So pandas, and then I'm also going to import Seaborn because I'm going to want that for this specific class. Okay. Great. So now our columns that we have in our seed data set are the area, the perimeter, the compactness, the length, width, asymmetry, groove, length, I mean, I'm just gonna call it groove, and then the class, right? The wheat kernels class. So now we have to import this. I'm gonna do that using pandas read CSV, and it's called seedsdata.csv. So I'm gonna turn that into a data frame. And the names are equal to the columns over here. So what happens if I just do that? Oops. What did I call this? Seeds dataset.text. All right. So if we actually look at our data frame right now, you'll notice something funky, okay? And here, you know, we have all the stuff under area, and these are all our numbers with some dash T. So the reason is because we haven't actually told pandas what the separator is, which we can do like this. And this T, that's just a tab. So in order to ensure that like all white space gets recognized as a separator, we can actually, this is for like a space. So any spaces are going to get recognized as data separators. So if I run that, now our, this is a lot better, okay? Okay. So now let's actually go and like visualize this data. So what I'm actually going to do is plot each of these against one another. So in this case, pretend that we don't have access to the class, right? Pretend that, so this class here, I'm just gonna show you in this example that like, hey, we can predict our classes using unsupervised learning. But for this example, in unsupervised learning, we don't actually have access to the class. So I'm gonna just try to plot these against one another and see what happens. So for some I in range, you know, the columns -1 because the class is in the columns. And I'm just gonna say for J in range, so take everything from I onwards, you know, so I, like the next thing after I, until the end of this. So this will give us basically a grid of all the different like combinations. And our X label is going to be columns I, our Y label is going to be the columns J. So those are our labels up here. And I'm going to use Seaborn this time. And I'm going to say scatter my data. So our X is going to be our X label. Our Y is going to be our Y label. And our data is going to be the data frame that we're passing in. So what's interesting here is that we can say hue, and what this will do is say, like if I give this class, it's going to separate the 3 different classes into 3 different hues. So now what we're doing is we're basically comparing the area and the perimeter, or the area and the compactness, but we're going to visualize, what classes they're in. So let's go ahead, and I might have to show. So great. So basically we can see perimeter and area, we get these 3 groups. The area compactness, we get these 3 groups, and so on. So these all kind of look, honestly, like somewhat similar, right? So, wow, look at this one. So this one, we have the compactness and the asymmetry, and it looks like there's not really, it just looks like they're blobs, right? Sure, maybe class 3 is over here more, but 1 and 2 kind of look like they're on top of each other, okay? There are some that might look slightly better in terms of clustering, but let's go through some of the clustering examples that we talked about and try to implement those. The first thing that we're going to do is just straight up clustering. So what we learned about was k-means clustering. So from sklearn, I'm going to import k-means. Okay. And just for the sake of being able to run, any x and any y, I'm just going to say, hey, let's use some x. What's a good one? Maybe, perimeter asymmetry could be a good one. So x could be perimeter, y could be asymmetry. Okay. And for this, the x values, I'm going to just extract those specific values. All right. Well, let's make a k-means algorithm, or let's, define this. So k-means. And in this specific case, we know that the number of clusters is 3. So let's just use that. And I'm going to fit this against this x that I've just defined right here. Right. So, if I create this clusters, so one cool thing is I can actually go to this clusters and I can say k-mean.labels, and it'll give me, if I can type correctly, it'll give me what its predictions for all the clusters are. And our actual, oops, not that. If we go to the data frame and we get the class and the values from those, we can actually compare these two and say, hey, everything, in general, most of the zeros that it's predicted are the 1s, right? And in general, the 2s are the 2s here. And then this third class 1, okay, that corresponds to 3. Now remember, these are separate classes. So the labels, what we actually call them, don't really matter. We can say, oh, map 0 to 1, map 2 to 2, and map 1 to 3. Okay, and our mapping would do fairly well. But we can actually visualize this. And in order to do that, I'm going to create this cluster data frame. So I'm going to create a data frame, and I'm going to pass in a horizontally stacked array with x. So my values for x and y, and then the clusters that I have here, but I'm going to reshape them so it's 2D. Okay, and the columns, the labels for that are going to be x, y, and class. Okay, so I'm going to go ahead and do that same seaborn scatter plot again, where x is x, y is y, and now the hue is again the class, and the data is now this cluster data frame. All right, so this here is my k-means, classes. So k-means kind of looks like this. If I come down here and I plot, my original data frame, this is my original classes with respect to this specific x and y. And you'll see that honestly, like it doesn't do too poorly. Yeah, the colors are different, but that's fine. For the most part, it gets information of the clusters, right? And now we can do that with higher dimensions. So with the higher dimensions, if we make X equal to, you know, all the columns except for the last one, which is our class, we can do the exact same thing. So here, and we can predict this, but now our columns are equal to our data frame columns all the way to the last one, and then with this class. Actually, so we can literally just say data frame columns. And we can fit all of this. And now, if I want to plot the k-means classes, all right, so this was my, that's my clustered and my original. So actually, let me see if I can get these on the same page. So yeah, I mean, pretty similar to what we just saw. But what's actually really cool is even something like, you know, if we change, so what's one of them where they were like on top of each other? Okay, so compactness and asymmetry. This one's messy, right? So if I come down here and I say compactness and asymmetry, and I'm trying to do this in 2D, this is what my scatter plot. So this is what, you know, my k-means is telling me for these two dimensions, for compactness and asymmetry. If we just look at those two, these are our three classes, right? And we know that the original looks something like this. And are these two remotely alike? No. Okay, so now if I come back down here and I rerun this higher dimensions one, but actually this clusters, I need to get the labels of the k-means again. Okay, so if I rerun this with higher dimensions, well, if we zoom out and we take a look at these two, sure, the colors are mixed up, but in general, the three groups are there, right? This does a much better job at assessing, okay, what group is what. So, for example, we could relabel the 1 in the original class to 2, and then we could make, sorry, okay, this is kind of confusing. But for example, if this light pink were projected onto this darker pink here, and then this dark one was actually the light pink, and this light one was this dark one, then you kind of see like these correspond to one another, right? Like even these two up here are the same class as all the other ones over here, which are the same in the same color. So you don't want to compare the two colors between the plots. You want to compare which points are in what colors in each of the plots. So that's one cool application. So this is how k-means functions. It's basically taking all the data sets and saying, all right, where are my clusters given these pieces of data? And then the next thing that we talked about is PCA. So PCA, we're reducing the dimension, but we're mapping all these 7 dimensions. I don't know if there are 7. I made that number up. But we're mapping multiple dimensions into a lower dimension number, right? And so let's see how that works. So from sklearn decomposition, I can import PCA, and that will be my PCA model. So if I do PCA component, so this is how many dimensions you want to map it into. And for this exercise, let's do 2. Okay, so now I'm taking the top 2 dimensions, and my transformed X is going to be PCA.fit transform, and the same X that I had up here. Okay, so all the values basically. Area, perimeter, compactness, length, width, asymmetry, groove. Okay, so let's run that. And we've transformed it. So let's look at what the shape of X used to be. So there, okay, so 7 was right. I had 210 samples, each 7 features long, basically. And now my transformed X is 210 samples, but only of length 2, which means that I only have 2 dimensions now that I'm plotting. And we can actually even take a look at, you know, the first 5 things. Okay, so now we see each one is a 2-dimensional point. Each sample is now a 2-dimensional point in our new dimensions. So what's cool is I can actually scatter these. 0 and transformed X. So I actually have to take the columns here, and if I show that, basically we've just taken this like 7-dimensional thing and we've made it into a single, or I guess a 2-dimensional representation. So that's the point of PCA. And actually, let's go ahead and do the same clustering exercise as we did up here. If I take the k-means, this PCA data frame, let's construct data frame out of that, and the data frame is going to be hstack. I'm going to take this transformed X and the clusters reshape. So actually, instead of clusters, I'm going to use k-means.labels, and I need to reshape this. So it's 2D, so we can do the hstack. And for the columns, I'm going to set this to PCA1, PCA2, and the class. All right. So now if I take this, I can also do the same for the truth, but instead of the k-means labels, I want from the data frame the original classes. And I'm just going to take the values from that. And so now I have a data frame for the k-means with PCA, and then a data frame for the truth with also the PCA. And I can now plot these similarly to how I plotted these up here. So let me actually take these two. Instead of the cluster data frame, I want the, this is the k-means PCA data frame. This is still going to be class, but now X and Y are going to be the 2 PCA dimensions. Okay. So these are my 2 PCA dimensions, and you can see that, you know, they're pretty spread out. And then here, I'm going to go to my truth classes. Again, it's PCA1, PCA2, but instead of k-means, this should be truth PCA data frame. So you can see that, like in the truth data frame, along these 2 dimensions, we actually are doing fairly well in terms of separation, right? It does seem like this is slightly more separable than the other like dimensions that we had been looking at up here. So that's a good sign. And up here, you can see that, hey, some of these correspond to one another. I mean, for the most part, our algorithm, our unsupervised clustering algorithm, is able to spit out, you know, what the proper labels are. I mean, if you map these specific labels to the different types of kernels, but for example, this one might all be the comma kernels, and same here, and then these might all be the Canadian kernels, and these might all be the Canadian kernels. So it does struggle a little bit with, you know, where they overlap. But for the most part, our algorithm is able to find the 3 different categories and do a fairly good job at predicting them without any information from us. We haven't given our algorithm any labels. So that's the gist of unsupervised learning. I hope you guys enjoyed this course. I hope, you know, a lot of these examples made sense. If there are certain things that I have done and, you know, you're somebody with more experience than me, please feel free to correct me in the comments, and we can all as a community learn from this together. So thank you all for watching.